The vacuum catastrophe. Amid the boundless stillness of the cosmos, where stars glimmer like remote beacons and galaxies sway gently in the rhythm of cosmic epochs, lies something that defies common sense, a phenomenon so perplexing it has left scientists puzzled for generations. It isn't a celestial body, neither a planet nor a star, not a nebula or a black hole. It's the void itself, the vacuum of space, and it conceals within it one of the deepest puzzles in contemporary physics. This riddle is known as the vacuum catastrophe, or more precisely, the cosmological constant dilemma. It's a paradox so deep it puts into question our fundamental grasp of existence itself. To begin unraveling this puzzle, we need to pose a seemingly obvious question. What exactly is nothing? At first glance, it appears self-evident. Nothingness is simply the lack of something, an absence, a blank. Yet in the language of physics, this notion is anything but straightforward. According to quantum field theory, even the most idealized vacuum, a region entirely void of particles or energy, is not truly barren. Instead, it is a restless sea of hidden activity, a churning foam where virtual particles emerge and vanish in an eternal quantum ballet. These particles and their antimatter counterparts appear spontaneously, collide briefly, and disappear, leaving subtle echoes in the vacuum. These entities aren't mere hypothetical constructs. They produce measurable outcomes. Consider the Casimir effect. When two neutral metallic plates are positioned extremely close together in a vacuum, they experience a minute attractive force drawing them inward. This attraction doesn't stem from any classical energy between the plates, but results from their disturbance of the quantum froth, leading to an imbalance in virtual particle interactions. Thus, if space is not empty, it must possess some intrinsic energy, a persistent murmur, a baseline level of reality. Physicists refer to this as vacuum energy, and despite its bizarre nature, it impacts the universe on an enormous scale. Back in 1917, Albert Einstein, in his attempt to portray the universe as steady and unchanging, introduced a peculiar element into his equations, the cosmological constant. This term represented a repelling force woven into the very essence of space, working against gravity to prevent a collapse of the cosmos. Einstein later regarded this as his biggest misjudgment, particularly after Edwin Hubble revealed that the universe wasn't stationary at all. It was expanding. Yet, many years later, this same cosmological constant re-emerged, this time to explain a far more bewildering phenomenon. In the late 1990s, two independent groups of astronomers observing far-off supernovae stumbled upon a stunning revelation. The universe's expansion isn't merely continuing, it's gaining speed. Galaxies aren't just moving apart, they're accelerating away from each other as time progresses. This finding flipped the field of cosmology upside down. Some unidentified force appeared to be driving the cosmos apart, a hidden pressure embedded in space itself. Scientists turned again to Einstein's abandoned constant, resurrecting it under a new name, dark energy. And here begins the conundrum. When researchers applied quantum field theory to calculate the vacuum's energy, the energy of apparent emptiness, the results were staggering. Theoretical estimates suggested that vacuum energy should be 120 orders of magnitude greater than what astronomical data shows. That's a difference so astronomically immense. It's like comparing a single atom to the entirety of the visible universe. In essence, the energy predicted by quantum physics and the energy we infer from observing the universe's expansion are catastrophically misaligned. This stark mismatch is what we now term the vacuum catastrophe, perhaps the largest numerical inconsistency ever encountered in the scientific world. How could two of our most robust theoretical frameworks, quantum mechanics, and general relativity, be so drastically at odds? This isn't merely an issue of mathematics. It's a profound inconsistency at the heart of our understanding of nature. Even a minute variation in vacuum energy, whether slightly stronger or weaker, would have rendered our universe unrecognizable. Galaxies might not have formed, stars might never have lit up, and life itself would have had no chance to arise. It appears that the vacuum energy is tuned with extraordinary precision, a coincidence so unlikely, it almost feels miraculous. Physicists have offered numerous ideas to explain it. One hypothesis suggests that our cosmos is but one of many, a multiverse populated by countless universes, each with distinct vacuum energies. In most, the energy might be so extreme it tears matter apart before anything can coalesce. But in our universe, by rare statistical fortune, the vacuum energy happens to be suitable for structure and life. Others argue that we might be missing an essential piece, a deeper, unifying principle that reconciles the discrepancies between relativity and quantum theory. Perhaps a yet undiscovered framework lies beneath, smoothing out the chaos and revealing a hidden harmony. Some researchers have looked to string theory, a complex tapestry of vibrating strands and hidden dimensions, for a possible solution to this dilemma. Yet, the vacuum catastrophe persists unresolved. It's as though the cosmos is holding a mirror to our own ignorance, forcing us to confront how much we have yet to learn about the nature of existence. Still, this puzzle also serves as a poignant reminder of something sublime, that even the void, even the seeming emptiness between the stars, is brimming with unknowns and latent wonder. You might ask, does this paradox hold any real-world significance? Or is it simply a theoretical headache for physicists to agonize over? The answer is both. If we manage to decipher the mystery of vacuum energy, if we can solve the cosmological constant riddle, we may not only untangle one of the most confounding enigmas in science, but also gain access to the inner workings of the universe itself. Could mastering vacuum energy lead to revolutionary technology, perhaps the ability to tap into the very energies of space-time? Could it reveal truths about the final destiny of the cosmos? Might the universe drift forever into stillness, fading into an eternal chill? Or will stranger phenomena take shape, driven by unseen currents in the fabric of the void? For now, the vacuum remains a paradox wrapped in silence, a seemingly empty stage filled with secrets our minds have only just begun to grasp. It reminds us that the universe is more than its stars and galaxies. It is also the invisible weave between them, the intervals where nothing appears to exist, yet everything is born. Perhaps the solution to this mystery lies in a yet unwritten equation, or in observations still to be made by the instruments of tomorrow. Until that moment arrives, each glance into the cosmic abyss echoes with the realization that the greatest truths may not reside in what is visible, but in the quiet spaces between, in the luminous stillness of the void, where one of nature's most profound secrets waits patiently to be discovered. The oh my God particle. Picture a lone proton, an unimaginably small subatomic unit, far tinier than an atom, racing through the endless void of outer space. Now envision this minuscule proton hurtling so rapidly, carrying such immense energy, that it could theoretically knock over a bowling pin from thousands of kilometers away, if it were ever to stop. This isn't the premise of a science fiction film. These particles are real. They're known as ultra-high energy cosmic rays, the swiftest and most enigmatic travelers in the universe. But where do they originate? How do they attain such mind-blowing levels of energy, surpassing what we can reach with even our most advanced particle accelerators? And perhaps the most perplexing question, How can they appear to disobey the established laws of physics? On the night of October 15, 1991, researchers using the Fly's eye detector in Utah registered an event so astonishing that they initially questioned if it was even legitimate. A single cosmic ray slammed into Earth's atmosphere, releasing an amount of energy on par with a baseball moving at 100 kilometers per hour. But this wasn't a baseball. It was a lone proton, so tiny it could glide through a human body without leaving a trace. They dubbed it the "Oh my God" particle, and not without cause. Its energy level was beyond anything previously recorded, over 300 million times more powerful than the protons accelerated in the Large Hadron Collider, leaving the physics community in disbelief. To offer a different comparison, if that proton were scaled up to the size of a tennis ball, it would be moving almost at the speed of light and carrying the force of a bullet fired from a gun. Here's where it becomes truly baffling. According to the current understanding of physics, such a particle should not even exist. The cosmic microwave background radiation, the faint thermal echo of the Big Bang, ought to act as a kind of friction, gradually draining energy from particles as they move across cosmic distances. And yet, this proton defied all of those expectations. Where could a particle like this possibly have originated? Cosmic rays are elusive by nature. They do not move in predictable lines. Instead, they ricochet and weave through the cosmos, distorted by interstellar magnetic fields. By the time they reach our planet, any trace of their starting point has long vanished. Still, scientists have some hypotheses. One possibility is that these rays are launched from the hearts of galaxies, where supermassive black holes dwell. As matter spirals into these immense gravitational wells, some of it is expelled in colossal jets moving at nearly the speed of light. Perhaps these jets function like gigantic slingshots, flinging particles across the cosmos at unimaginable speeds. Another potential source is gamma-ray bursts, the most violent known explosions in the universe. These momentary eruptions are so intense they can outshine entire galaxies for brief moments. If cosmic rays are born in such explosive phenomena, they might carry signatures of that violent origin. However, neither theory fits seamlessly. The directions from which these ultra-high energy cosmic rays arrive don't consistently point toward active galactic cores or known gamma-ray bursts. It's as if these particles are deliberately hiding their tracks, moving through space like silent cosmic hitmen, leaving no clues about where they began their journey. To investigate further, researchers have established enormous detection facilities like the Pioneer Anomaly Observatory in Argentina. This site covers over 3,000 square kilometers with specialized detectors designed to track these high-energy events. When one of these particles enters Earth's atmosphere, it triggers a cascade of secondary particles, a radiant shower that the instruments can pick up and record. Despite years of data collection, the enigma remains. A theoretical boundary known as the Greisen-Zatsepin-Kuzmin-GZK limit defines a ceiling for how much energy a cosmic ray can retain over long distances. According to this idea, high-energy particles should gradually lose their punch as they collide with the cosmic microwave background, the lingering heat from the birth of the universe. In short, any particle that's traveled far enough shouldn't still carry such tremendous energy. And yet, certain ultra-high energy cosmic rays clearly violate this limit. If they come from nearby, we should have identified their origins by now. If they're from far away, they shouldn't still be so powerful. It's as though the universe is operating under a rulebook we haven't yet discovered. Some theorists have even speculated that these rays might be hinting at unknown physics, concepts beyond our current scientific framework. One theory proposes that the particles aren't protons at all, but strangelets, hypothetical forms of matter composed of unusual types of quarks. Others suggest these rays could be leaking in from alternate universes, slipping across the thin boundaries that might separate different realities. Then there's an even more radical notion that these particles may be pointing out flaws in our understanding of spacetime itself. Could it be that the universe has concealed dimensions or unfamiliar physical laws that only become visible at these extraordinary energy scales? Ultra-high energy cosmic rays aren't just fascinating oddities. They might be messengers, carrying encrypted messages from the farthest reaches of the universe. Each one that strikes Earth's atmosphere could be a fragment of a cosmic narrative stretching back billions of years. Yet the story remains incomplete. The source of these mysterious particles is still a blank space. Their seemingly impossible energies remain without a definitive explanation. And each time we capture one, we're reminded just how much about the universe we still don't comprehend. Maybe the next incoming particle will hold the missing piece of the puzzle, or perhaps it will deepen the mystery further. For now, the sky remains serene, dotted with stars, and somewhere out there, in the cold, dark vacuum, another ultra-high energy cosmic ray is on its way, traveling toward us with the power of 1,000 suns, bearing a secret we have yet to unlock. The ultimate theory. At the core of every scientific mystery, beneath layers of formulas and distant star systems, lies a single captivating vision, a vision of perfect unity, a belief that deep within the mathematical structure of existence, there resides one equation, one profoundly elegant principle that can explain everything, every galaxy, every atom, every force of nature, and every fleeting instant of time, all expressed in one unified system. This is the pursuit of the theory of everything. It's an idea so daring, so sweeping in scope, that it borders on legend. And yet, for physicists, it represents the most coveted achievement of all, the ultimate solution to the most fundamental mystery, why the universe operates the way it does. To grasp the meaning of this pursuit, we need to return to an earlier era, when the field of physics was fragmented into separate territories, each governed by its own distinct rules. On one side, there was the realm of the immensely large galaxies, black holes, and the warping of space and time. This domain followed the rules of Albert Einstein's general relativity, where gravity isn't a pulling force, but the curvature of spacetime itself. On the opposite end was the domain of the minuscule, particles, fields, and quantum uncertainties, a bizarre and unpredictable world ruled by quantum mechanics, where electrons hover in clouds of possibility, particles can pass through barriers, and certainty gives way to probability. Both of these theories are remarkably accurate. General relativity allows us to precisely predict planetary movements and the bending of starlight. Quantum mechanics, on the other hand, is the foundation of chemistry, material science, and the very devices you're using to access this message. Yet despite their individual triumphs, they refuse to work together. When scientists try to merge general relativity with quantum mechanics, the mathematics collapses. The equations produce infinite results. Contradictions emerge. The logical consistency of both systems breaks down entirely. It's like trying to merge two maps, one showing continents from above, the other showing the detailed layout of a single neighborhood. Both maps are valid in their respective scopes, but when combined, they don't align. The search for a theory of everything is really an effort to reconcile this contradiction, to create a model that can describe all of reality, from the gravity-drenched cores of black holes to the restless energy of subatomic particles. One of the most hopeful proposals for this unifying theory appeared toward the end of the 20th century and was given a poetic name: string theory. The essence of string theory is that the most fundamental components of nature are not particles, but minuscule vibrating strings, tiny loops of energy oscillating in various patterns. Just as the strings of a musical instrument can produce different notes depending on how they vibrate, these fundamental strings generate different particles based on their unique vibrational modes. Electrons, quarks, photons, rather than separate entities, they are different vibrations on the same universal string. It's a graceful and mesmerizing idea, deeply mathematical, resonant, and yet it introduces new challenges. String theory cannot function in our standard four-dimensional universe, three of space and one of time. It necessitates the existence of additional dimensions, hidden realities that are compacted so tightly we cannot perceive them. 10 dimensions, maybe even 11, realms within realms, tucked away like folded pages inside the cosmos. For decades, physicists have explored string theory, crafting sophisticated mathematical frameworks and hunting for testable predictions. But thus far, the proof remains out of reach. The strings, if they exist, are too microscopic to detect. The extra dimensions remain concealed, tightly wrapped within spacetime. Even so, string theory isn't the only theory in contention. An alternative known as loop quantum gravity offers a different path. Instead of positing strings, it proposes that space and time themselves are granular, made up of tiny, indivisible loops. Imagine space as a digital screen where each pixel is a fundamental unit of geometry. These loops construct the very structure of the cosmos. Both string theory and loop quantum gravity attempt to address the same fundamental issue. What constitutes the true substance of reality? Yet perhaps the difficulty doesn't lie in our models, but in the assumptions we make. What if the universe isn't governed by a tidy, overarching law waiting to be unveiled? What if our longing for simplicity and elegance is more a reflection of the human mind than of nature itself? The effort to discover a theory of everything is not merely a scientific endeavor, it's philosophical. It questions whether the universe must be comprehensible to us, or whether it simply exists without the obligation to be understood. Are we chasing an illusion? Or are we genuinely nearing the most profound insight science has ever known? For some physicists, like Stephen Hawking, this question had a personal dimension. Hawking devoted much of his life to this pursuit, convinced that one day humanity might grasp what he called the mind of God. Yet, as time passed, Hawking began to question whether such a theory could ever be found. Maybe the cosmos isn't unified by a single rule, but assembled from overlapping laws, more a mosaic than a singular monument. Still, the search pushes onward, in underground particle accelerators, in equations written on late-night chalkboards, and in the subtle tremors of gravitational waves echoing through the cosmos. Each new discovery offers progress and reveals how much remains unknown. But perhaps the true wonder of the theory of everything isn't in arriving at the final equation. Maybe it lies in the very act of pursuit, in the courage to ask questions of such vast scale, and in the boldness to imagine that we, tiny beings on a fragile planet circling an ordinary sun, could someday understand the entire cosmos. Whether or not we ever arrive at the ultimate formula, the quest has changed us. It's revealed the intricate nature of the universe, the beauty hidden in disorder, and the mysterious elegance that lies at the foundation of all things. And perhaps, someday, someone will scrawl a short series of symbols on a board, an equation that holds within it all things: the stars, the galaxies, the particles, the waves, and every fleeting instant of time. A kind of cosmic Rosetta Stone, unlocking the deepest mysteries of existence. But until that moment, the question remains unanswered. Is there a definitive explanation for everything? Or will the universe always hold back a part of itself, an eternal secret whispered through the silence of space? In the end, the theory of everything isn't only about understanding the cosmos. It's about understanding ourselves, why we question, why we imagine, why we gaze into the night and feel drawn to something immense, mysterious, and yet strangely familiar. The existence of the universe. Why is there anything rather than absolute emptiness? It's a question so immense, so deeply foundational that it feels nearly unanswerable. Yet it's a question that murmurs within us, a quiet echo from the edges of our thoughts when we look up into the dark sky. Each galaxy, every star, every flash of light exists, and the mere reality that anything exists at all might be the most staggering mystery of them all. At its essence, this question shakes the very foundation of what we believe we understand. If everything in the universe follows physical principles, then what is the origin of those principles? If the Big Bang marked the birth of both time and space, what preceded that moment? And why did reality take a shape that made matter, galaxies, worlds, and ultimately life itself possible? To even begin tackling this, we must start with what science currently tells us. The Big Bang, roughly 13.8 billion years ago, the universe burst forth from an unfathomably hot, dense point. In those first fractions of a second, time and space unfurled, energy turned into matter, and the basic ingredients of the cosmos began to form. But what ignited this event? Was it a spontaneous occurrence within a quantum field? Was it a deterministic outcome, something bound to unfold eventually, given infinite possibilities? Or did it stem from something so far beyond our comprehension we can barely frame it? Physicists frequently look to quantum mechanics, with all its paradoxes, for potential explanations. In that strange subatomic world, particles can appear and disappear without an apparent cause. What we think of as empty space is actually full of restless activity, particles and their opposites briefly flaring into being before canceling each other out. Could it be that our entire cosmos came into existence due to one such quantum fluctuation? A temporary disturbance in a backdrop of apparent nothing? If so, then perhaps nothingness isn't true emptiness. Maybe it's a churning sea of possibilities, where new universes spontaneously arise like bubbles forming in a vast cosmic froth. And yet, even if that theory holds, we're left grappling with the same dilemma. Why does this quantum nothing even exist? Some scientists look toward the idea of a multiverse for perspective. In that scenario, our universe is just one of many, perhaps even an infinite number, each governed by different laws, constants, and initial conditions. Maybe new universes are born all the time, and ours simply happens to be one with just the right setup for matter to gather into stars and life to eventually emerge. But even this grand idea feels like a kind of detour. Why would the multiverse itself exist? Why is there anything at all? In the 18th century, philosopher Gottfried Wilhelm Leibniz famously posed this very question. His answer was among the most poetic. He proposed that the universe exists because it is the finest of all conceivable realities, a cosmos born from some inherent principle of perfection. Interestingly, this notion has found resonance in aspects of modern theoretical physics, where some theorists speculate that the physical laws of our universe are just right because they had no choice but to be, not necessarily the result of a designer, but perhaps a mathematical necessity, an inevitable configuration stitched into the nature of existence itself. But then, there's a different, more disquieting possibility. What if the question we're asking is fundamentally flawed? What if inquiring why the universe exists is like asking what lies beyond the northernmost point of the North Pole? Some scientists argue that cause and effect, the concept that every result must follow from something else, might not even apply at the origin of the universe. Time, space, and causality themselves came into being with the Big Bang. To ask what came before might be meaningless, because there was no before. Still, even with this reframing, the riddle lingers. Behind every scientific discovery, every tidy formula, lies a deeper question. Why these specific physical laws? Why this version of the universe, and not a complete void? It's entirely possible that we will never uncover the answer, that the question of why there is something instead of nothing is simply beyond our reach, a puzzle without a solution, an eternal cosmic secret. Yet, in a strange way, that feels oddly appropriate. The fact that we, complex arrangements of atoms and energy, are even capable of wondering about this question is extraordinary on its own. That human minds, shaped by stardust and natural selection, can peer across eons and ponder the mystery of their own existence is astonishing. And maybe, just maybe, the act of asking is itself the point. Perhaps the universe exists so that such questions could be raised, so that awareness could emerge and contemplate the strange, improbable beauty of it all. So why does anything exist? For now, it remains the greatest question of them all, a mystery etched into the stars, humming through atoms, and reflected in every fleeting breath of our existence. Proton decay. In the silent stretches of deep time, beneath the layers of what we perceive as reality, where protons and neutrons form the threads that hold the universe intact, a quiet countdown may be unfolding. It's a timer so subtle, so slow-moving, that it nearly escapes detection. This countdown is interwoven into every atom in your body, each droplet of water, every star above. It is the enigma of proton decay, one of the most puzzling unanswered questions in contemporary physics. Protons form the essential core of matter. They are the nucleus of atoms, anchoring electrons in orbit and giving tangible form to all that we can observe and touch. By every practical measure, protons appear indestructible. They show no signs of aging or deterioration. They do not decay, or at least, that's how it appears based on current scientific observations. But what if that's not the full truth? What if, given an immeasurably long timeline, even protons, the foundational pillars of matter, are destined to break apart into something new? If proton decay is real, its implications are vast. It suggests that the universe is not built to last forever. Even its most fundamental units carry a finite lifespan, a point where they collapse into more elementary, less tangible forms. It would mean that all things, galaxies, suns, atoms, will eventually dissolve into emptiness. And yet, despite decades of intense research, not a single confirmed instance of proton decay has ever been recorded. To grasp the significance of this mystery, we must turn back to the bedrock of modern particle physics, the Standard Model. This framework represents our most refined understanding of matter at the smallest possible scales. It describes quarks and leptons, photons and gluons, the unseen forces and particles that bind the physical world together. According to the Standard Model, protons are eternally stable. But physics doesn't stop there. There are theories that go beyond the Standard Model, ambitious attempts to combine the universe's four known forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These attempts are known as Grand Unified Theories, or GUTS. In these deeper models, protons are no longer immortal. They can, theoretically, decay. Picture a proton nestled at the heart of an atom. After an inconceivably long duration, possibly once in every 10 circumflex 34 years, it undergoes a rare transformation. In that moment, it disintegrates, releasing a flurry of strange particles. The specifics vary depending on the theoretical framework, but many predict that the proton would decay into a positron, a positively charged counterpart of the electron, and a neutral pion, which would itself rapidly break down into gamma rays, or bursts of light. The death of a single proton would be nearly invisible, a gentle flicker lost in the vast dark. But if it were to happen across all protons throughout the universe, it would signal the slow disintegration of matter itself. And yet, the conundrum persists. We have never witnessed such a decay. Physicists have constructed vast, subterranean laboratories to hunt for the signs. They shield these detectors from background interference, cosmic radiation, and every possible false signal. One prime example is the Super Kamiokande experiment in Japan, a massive chamber holding 50,000 tons of ultrapure water, buried far beneath the Earth. It is surrounded by thousands of ultra-sensitive sensors, constantly watching, waiting, hoping to detect the dim glow of a proton's final moment. Years have passed, decades, even, and the detectors have seen nothing. Does this mean protons truly last forever? Or are we simply missing the signs? Maybe our instruments are still inadequate. Perhaps our theories are flawed. It could be that protons do decay, just not in ways we currently understand, or on timelines that are so astronomically long they exceed the limits of our measurement. The pursuit of proton decay goes far beyond particle physics. It touches on the ultimate destiny of the cosmos. If protons truly endure, then matter itself could persist indefinitely. Stars may extinguish, galaxies might scatter, but the protons would remain, a silent, unchanging ocean of particles adrift in the blackness. But if they decay, then the universe has a final, definitive ending. In the far future, long after the last stars have dimmed and black holes have vanished, the closing act of reality would be the slow, quiet disintegration of protons. Bit by bit, molecule by molecule, the very essence of existence would unravel into energy, fading into a cold, thin haze of photons and neutrinos. The implications are staggering. The timescales are almost beyond human comprehension. And still, physicists continue the search. Why? Why dedicate decades of effort, invest billions, and pour endless hours into chasing a signal so faint it borders on the undetectable? Because this is about more than particles. It's about the universe itself, what it is, how it changes, and what role we play within it. If protons are destined to decay, it means the universe is not static. It evolves, it transforms, on timescales that dwarf our lifespans. And if protons are perfectly stable, then we must ask, what grants them this stability in a cosmos otherwise defined by entropy and transformation? Every silent detector in a cavern beneath the ground, every faint photon captured, every complex equation chalked onto a board, each one is part of a larger narrative, a story about the deepest rules of existence, a story that asks whether reality concludes with a final page or drifts onward without end. Somewhere, hidden in the data we've gathered, or buried in formulas we've yet to write, the answer is waiting. It may be hidden in a faint flash of light deep below the Earth's surface, a fleeting signal from a decaying proton, or it might lie in an undiscovered theory, one that rewrites everything we believe to be true. For now, the protons inside your body remain unshaken. They continue to hold your atoms in place, silently maintaining the architecture of your existence. But somewhere, perhaps in a distant sun, perhaps deep below the Earth, or drifting through the emptiness of space, one proton could already be living out its final moments. Matter-antimatter asymmetry. The universe, as it currently exists, defies what physics predicts. It shouldn't be filled with galaxies spinning in the vast darkness, nor with stars radiating from nuclear fusion, nor planets revolving in calm harmony, and certainly not with you listening to these words. According to the fundamental principles of physics, every piece of matter, protons, neutrons, electrons, should have been exactly paired with an equivalent antimatter particle, a proton mirrored by an antiproton, an electron paired with a positron. And when these pairs encounter each other, they obliterate one another in a release of pure energy, leaving behind only light. If the cosmos had followed these rules flawlessly, there would have been no stars, no worlds, and absolutely no life. Only a cold, lifeless expanse and the faint echo of annihilation would remain. But clearly, that outcome was not our reality. Something, at some point, disrupted the perfect symmetry. Somehow, matter gained the upper hand. We now live on the leftover sliver of that early imbalance. Out of every billion matter-antimatter duos that formed during the universe's infancy, a single extra matter particle survived. From that minuscule asymmetry, everything emerged. Galaxies, stars, swirling nebulae, and even the atoms that make up your body. But the question remains, why? What transpired in those first fleeting instants that nudged the universe toward matter? And how did such a microscopic discrepancy yield everything that now exists? To search for answers, we must venture back, not just to the Big Bang, but to the chaotic, overheated conditions that immediately followed. In those early fractions of a second, the cosmos was a roiling soup of particles flickering into and out of being. Energy and mass were interchangeable, and balance reigned. Yet as expansion and cooling set in, something unusual occurred. That symmetry cracked. The even match between matter and antimatter was ever so slightly disturbed, and within that fracture lies the secret to our existence. In the 1960s, Soviet physicist Andrei Sakharov proposed a foundational framework explaining how this asymmetry might have emerged. He outlined three essential conditions that had to be satisfied in the universe's early stages. First, there needed to be a fundamental difference in how matter and antimatter behaved, a breach in what's known as CP symmetry. Second, the universe had to exist in a state of disequilibrium, an unstable environment where particles and antiparticles didn't equally interact. Third, there had to be mechanisms that could produce more matter than antimatter through these skewed interactions. This concept sounded theoretically straightforward, but detecting these violations turned out to be exceptionally difficult. Then, in 1964, physicists James Cronin and Val Fitch made a breakthrough that shook the very foundations of particle theory. While studying a type of particle called a kaon, they discovered a faint but unmistakable violation of CP symmetry. Kaons and their antiparticles did not behave identically. It was the first concrete proof that the laws of nature held a slight preference for matter. However, the scale of that CP violation was far too minor to explain the universe as we see it today. It was like spotting a scratch on a skyscraper and claiming it explained why the entire building collapsed. Clearly, there was more to uncover. In more recent years, researchers have turned their focus toward one of the universe's most enigmatic particles, the neutrino. These ghost-like entities pass through almost all matter undetected. Trillions are moving through your body as you read this. Some theoretical models propose that neutrinos might hold the answer to this cosmic mystery. If neutrinos are Majorana particles, meaning they are their own antiparticles. They could have decayed in the early universe in a manner that subtly favored matter. This process, called leptogenesis, might have seeded the slight imbalance that ultimately led to all of existence. But attempting to study neutrinos is like trying to grasp mist with your bare hands. Massive detectors buried deep underground, shielded from the noise of the surface world, are meticulously monitoring for even the faintest sign of neutrino behavior that could support this idea. Still, the evidence remains just beyond reach. Faint murmurs in the dark, whispers buried in noise. Another idea, both daring and unsettling, suggests a radically different possibility. What if antimatter hasn't disappeared at all? What if it simply exists elsewhere? Some physicists speculate that vast regions of the cosmos might be composed entirely of antimatter, antimatter stars, antimatter galaxies, perhaps even antimatter worlds. If such domains do exist, they would be separated from matter-dominated regions by immense voids. Because where matter and antimatter touch, annihilation ignites, releasing energy in brilliant displays. But here's the catch. We've never observed such fireworks. The gamma-ray signatures that would mark large-scale matter-antimatter collisions are nowhere to be found. If antimatter still exists, it has left no visible trail. And so, the puzzle deepens. Somewhere in the mathematical language of particle physics, in the decay patterns of kaons, in the nearly invisible traces of neutrinos, or perhaps scattered across the vastness of space, the answer waits. A revelation that could explain not just the presence of matter, but our very presence. It's remarkable to consider that everything, the stars, the galaxies, all of life on our planet, traces its origin back to a flaw, a minute imperfection in the initial conditions of the universe. The cosmos broke its own symmetry, and that break gave birth to everything. But was it really chance? Was it nothing more than a statistical accident, a random flip of a cosmic coin that just happened to favor matter? Or does something deeper lie beneath it, a fundamental principle embedded in the laws of nature, a reason for matter's victory over antimatter? As of now, the answer remains concealed, hidden within the results of collider experiments, the readings from space observatories, and the quiet measurements of underground neutrino labs. But with each observation, with every particle collision, and every flash of data, we inch closer to understanding the unbalanced equation that sparked creation. One day, the cosmos might yield its secret, and when it does, we may finally comprehend why there is something rather than nothing at all. The quantum measurement conundrum. In the unseen realm of the minuscule, where particles flicker into and out of being, where chance governs over predictability, and where existence itself seems to gamble, there exists a dilemma so confounding, so foundational, that it unsettles our most basic beliefs about what it means to witness the universe. It is known as the quantum measurement problem, and it is far more than just a technical challenge reserved for physicists. It is a deep philosophical riddle that strikes at the very essence of reality. At the center of this enigma lies a concept so strange, so contrary to intuition, that it has left both scientists and philosophers puzzled for more than 100 years. To grasp its implications, we must venture into the curious domain of quantum mechanics, a framework that defines how particles behave at unimaginably small scales, where electrons circle atomic nuclei, photons glide through the void, and classical physics gives way to a mist of statistical likelihoods. In the early decades of the 1900s, pioneering physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger uncovered a remarkable truth. Particles at the quantum level do not resemble tiny billiard balls bouncing in predictable trajectories. Rather, they manifest as waves of probability, mathematical patterns that encapsulate all possible results. Consider an electron. It does not possess a precise location or speed until we attempt to observe it. Before any measurement, it exists in a state of superposition, simultaneously present everywhere and nowhere. This isn't mere speculation. We've confirmed it through experiment. Look to the iconic double-slit experiment. When researchers aimed individual electrons at a screen with two narrow openings, they anticipated the electrons to go through one slit or the other, forming two distinct marks on the back wall. But instead, an interference pattern emerged, implying that each electron behaved like a wave, traveling through both slits at once. Then came the twist, when scientists placed a detector near the slits to identify which path each electron took. The interference vanished. The electrons no longer acted like waves. They picked a side, like particles. Observation, it seemed, compelled the electron to decide. And this is the heart of the quantum measurement problem. How does the act of measurement, or observation, cause a quantum system to collapse from a wave of possibilities into a single, defined result? What does it mean to observe something in this framework? Is it a conscious mind perceiving the system? Is it merely interaction with an instrument? Or is it something even more fundamental, embedded in the universe itself? To unravel this mystery, physicists have suggested a variety of interpretations, each one more intriguing than the last. One of the earliest and most well-known is the Copenhagen interpretation, advocated by Bohr and Heisenberg. It proposes that quantum systems lack definite properties until they are observed. The wave function, the mathematical depiction of a quantum state, contains all potential outcomes, and only through measurement does one possibility become real. But this leads to a troubling query. What exactly constitutes a measurement? A human mind? A device? Or just any interaction with the surrounding environment? In 1935, Schrödinger emphasized the oddity of this view with a thought experiment that has since become legendary: Schrödinger's cat. Picture a cat sealed inside a box with a poison that will be released if a radioactive atom decays. A purely probabilistic event. According to the Copenhagen view, until the box is opened and the cat is observed, it remains in a superposition, both alive and dead. Disturbing as it is, this illustrates the core of the issue. How does the fuzzy, indefinite nature of the quantum world transform into the definite, crisp reality we live in? An alternative explanation is the many worlds interpretation, introduced by Hugh Everett III in the 1950s. This theory asserts that every time a quantum event is measured, the universe splits into several versions, each reflecting a different possible outcome. In one branch, the cat survives. In another, it perishes. Under this perspective, the wave function doesn't truly collapse. It diversifies into countless parallel worlds. While the concept is compelling, it comes with the hefty cost of proposing infinite, unseen universes, each home to its own reality. Other theories, like the pilot wave theory or quantum decoherence, try to address the measurement issue from different angles. Decoherence, for instance, argues that interaction with the environment locks quantum systems into specific states, bypassing the need for an observer. But even this leads to new puzzles. What really defines a measurement, and how does it shape what we call real? Ultimately, the quantum measurement problem is not just about subatomic particles, interference patterns, or differential equations. It is about the boundary, fragile and uncertain, between the quantum realm and the classical one, between chance and certainty, between what could be and what actually is. And somewhere in that boundary may rest the key to answering one of science's greatest questions. What is the fabric of reality truly composed of? The implications go far beyond physics. They touch philosophy, consciousness, even the nature of awareness itself. When you gaze up at the night sky, are you collapsing the quantum states of those distant stars into fixed locations? Are you, perhaps, helping to shape the universe merely by perceiving it? As of now, the quantum measurement problem remains unresolved. But with every electron fired through a slit, with every entangled particle manipulated in a quantum processor, and with every effort to examine the fabric of spacetime, we inch closer to an answer. Perhaps the cosmos itself is a vast quantum trial, a grand experiment, patiently awaiting a moment of observation. Or maybe the solution lies not among the galaxies or the atoms, but in the narrow gap between them, in the delicate act of measurement itself, where endless possibilities condense into the fleeting clarity of the present. One day, we might comprehend why looking changes what is seen, why particles select a path, and whether reality branches endlessly or simply settles into a single truth. Until then, the quantum measurement problem stands as a monument to the idea that at nature's most fundamental level, certainty is an illusion, and understanding is always just beyond our reach. And maybe, just maybe, that's the most breathtaking mystery of all, that in the shimmering fog of probability, reality is still waiting for someone to witness it. White holes. In the vast stage of the universe, black holes are among its most mysterious figures, bottomless voids where gravity dominates entirely and not even light can break free. These cosmic traps act as irreversible gateways, places where time stretches and matter encounters an unknowable end. But what if there existed another kind of passage? Not an entrance, but an exit, a theoretical opposite of a black hole, a phenomenon through which nothing enters, only exits? These imagined entities are referred to as white holes. At first mention, white holes might seem more like the stuff of fantasy than real science. They are theoretical constructs, relatives of black holes, arising from the same foundational mathematics in Einstein's theory of general relativity. While black holes have been observed throughout the cosmos, white holes remain purely hypothetical. Perhaps they don't exist at all. And yet, they continue to captivate theoretical physicists. To grasp the notion of white holes, one must begin by understanding black holes. In 1915, Albert Einstein introduced his theory of general relativity, a groundbreaking formulation that reshaped our view of gravity, space, and time. Shortly after, physicist Carl Schwarzschild provided a solution to Einstein's equations for a particularly extreme case: the gravitational collapse of a massive body into a point of infinite density, a singularity. This solution, known as the Schwarzschild metric, was the first mathematical model of a black hole. However, embedded in that solution was an unexpected and bizarre possibility, a second outcome with mirrored temporal characteristics. Instead of drawing matter inward, this model described an entity that expelled everything outward. Instead of acting as a cosmic snare, it functioned as a cosmic geyser. Without intending to, Schwarzschild's equations had forecasted the existence of white holes. Unlike black holes, which form naturally from the collapse of massive stars, and for which we have overwhelming observational evidence, white holes face a fundamental obstacle. There is no apparent mechanism for their formation. A black hole results when a star exhausts its fuel and collapses under its own gravity, compressing into a singular point. But a white hole would need to come into existence fully intact, without having absorbed anything. Rather than drawing in matter, a white hole would be permanently sealed from outside interaction, a kind of cosmic fountain flowing only outward. Imagine watching a waterfall run in reverse. In the real universe, this contradicts the second law of thermodynamics. the principle stating that entropy, or disorder, must always increase. A white hole constantly emitting matter and energy in an organized way would imply a system where entropy decreases, something that contradicts our current understanding of physics. Still, the mathematics remains firm. White holes are permitted by the equations. Gamma ray bursts, brief, powerful flashes of high-energy light, are among the most energetic events we've detected. Their origin remains partly unknown, and some scientists have proposed a bold theory. Could these bursts mark the death throes of white holes? Could they represent the final moments of ancient white holes vanishing from reality? It's speculative, highly so, but not entirely illogical. If white holes did exist, we would expect them to appear explosively, erratically, and unlike anything else. And then, the questions get even more bizarre. What if black holes and white holes aren't two different things, but connected? Two ends of a tunnel through space and time, a bridge, or wormhole, linking a black hole's singularity to a white hole's ejection point in another part of the universe, or perhaps in another universe entirely. This idea comes from the concept of the Einstein-Rosen bridge, a hypothetical tunnel through spacetime suggested by general relativity. Under this idea, each black hole might have a white hole counterpart, connected by such a wormhole. But there's a problem. These wormhole links are profoundly unstable. A slight disturbance, even a single photon, would collapse the passage instantly, making it impossible to traverse. Still, the idea endures. Matter absorbed into a black hole could, in theory, be expelled somewhere else, sometime else, through a white hole. Another possibility is just as strange. Black holes don't last forever. Over immense timescales, they evaporate due to a phenomenon called Hawking radiation, a faint emission of energy from their event horizons. As a black hole diminishes, inching closer to extinction, could it eventually flip? Could its final phase trigger a transformation into a white hole, ejecting its imprisoned contents in a final chaotic explosion? This theory combines elements of black holes, white holes, and quantum physics into a single stunning proposition. At its core, the mystery of white holes may not stem from general relativity at all. It may be rooted in the unresolved realm of quantum gravity, the long-sought theory that merges Einstein's grand cosmological framework with the unpredictable world of quantum mechanics. Some physicists believe that white holes might emerge at quantum scales, infinitesimally small and fleeting, forming and vanishing in sync with the foamy, jittering texture of spacetime. They could be leftovers from the universe's birth, tiny relics of the Big Bang scattered throughout the cosmos. But without a completed theory of quantum gravity, these ideas remain speculative shadows, projections on the wall of our limited understanding. After 100 years of contemplation, white holes remain trapped in the domain of theoretical physics. They are elegant mathematical ghosts, etched into the equations, yet absent from direct observation. Perhaps they are fundamentally impossible, forbidden by nature's deeper laws. Or perhaps they exist, hidden in the unseen corners of the universe, elusive and rare, awaiting discovery. Even if white holes never turn out to be real, their study teaches us something remarkable. The cosmos is not just odd, it's far more strange than we can fathom. Somewhere, buried in the equations of relativity, in the brief flashes of gamma ray bursts, or in the final whispers of dying black holes, a truth may be waiting. For now, the riddle of white holes stands as an unanswered question, a doorway we have yet to cross. The multiverse hypothesis. The cosmos is enormous, so vast, in fact, that it surpasses the capacity of the human mind to fully comprehend. Trillions of galaxies exist, each one harboring billions of stars, all scattered throughout a boundless cosmic domain. Yet even this incredible enormity may represent only a minuscule portion of the greater picture. What if our universe isn't the universe? What if it's merely one small droplet within a limitless sea of universes, each shaped by its own physical principles, its own spatial dimensions, its own peculiar form of existence? This concept is known as the multiverse hypothesis, the proposition that our universe is not solitary, but rather one volume in an infinite anthology of cosmic stories. But where did such an idea originate? How did logical, evidence-driven scientists, grounded in mathematical reasoning and empirical methods, come to consider such an extraordinary notion? It began with a surprising development in the field of cosmology, inflation theory. In the early 1980s, physicist Alan Guth introduced a bold new concept to resolve several of the most confounding mysteries about the universe's earliest moments. According to Guth, in the tiniest sliver of time following the Big Bang, the universe underwent a sudden and extraordinary expansion. This fleeting episode, known as inflation, caused space itself to grow at a rate faster than the speed of light. Inflation offered explanations for several cosmic puzzles: why the universe appears so even and consistent on the largest scales, and why far-flung regions exhibit nearly identical temperatures despite never having interacted. It was a compelling theory, simple and potent. Yet inflation also came with an unusual consequence. It might never have truly ended. In Guth's framework, inflation isn't a singular event, it's an ongoing process. Isolated regions of space cease inflating and stabilize, forming distinct universes, like individual bubbles forming on the surface of boiling water. Meanwhile, the broader cosmic broth continues to expand without end, spawning more and more bubbles, each a separate universe, each with its own attributes, its own natural laws. In this scenario, our universe is just one among countless bubbles within a sprawling cosmic foam. Inflation, however, is not the only gateway to the multiverse. Quantum mechanics, the science that governs the behavior of the smallest known particles, offers another perspective into this astonishing possibility. In the 1950s, physicist Hugh Everett introduced the many worlds interpretation of quantum mechanics. At the heart of this idea lies an unsettling implication. Every quantum event gives rise to multiple outcomes, and each outcome spawns a new, separate universe. Picture flipping a coin. In one universe, it lands heads. In another, it lands tails. Every quantum interaction, every decision, every potential event causes the universe to divide, resulting in an endless series of branching realities, each as tangible as the one we occupy. In one reality, you may have stayed indoors today. In another, you stepped outside and met a stranger who forever changed your life. It's mind-bending, nearly impossible to fully grasp, and yet it flows directly from the mathematics underpinning quantum theory. Then there's string theory, a theoretical framework aiming to unify all fundamental forces into a single, elegant formulation. According to this theory, reality doesn't consist of just three spatial dimensions. Instead, it operates within 10 or even 11 dimensions, depending on the specific model. These hidden dimensions are compacted into shapes so small they evade detection, but they are essential. They influence everything, from the strength of gravity to the behaviors of subatomic particles. Here's the surprising twist. String theory doesn't describe one universe. It predicts a landscape, a vast range of possible universes, possibly numbering 10 circumflex 500, each with different configurations of physical laws. Gravity may be weaker in one universe, stronger in another. In some, stars may never form. In others, unfamiliar forms of matter and energy may dominate. If the multiverse is real, it could provide answers to one of the most profound riddles in physics, the fine-tuning problem. Why are the fundamental constants of our universe, the speed of light, the electron's charge, the gravitational constant, so precisely tuned to permit life? Slight changes in any of these values would prevent stars from igniting, halt planetary orbits, or disrupt complex chemistry. The multiverse offers a solution. Our universe isn't uniquely designed for life. It just happens to be one of the rare few among endless alternatives where the constants allow life to emerge. But this leads to a crucial challenge. How can it be tested? Science is rooted in observation, in experimentation, in the requirement that theories must be falsifiable. The multiverse, by definition, lies beyond our observational reach. We cannot see other universes. We cannot interact with them, measure them, or verify them through direct evidence. To some researchers, this means the multiverse isn't truly a scientific theory, at least not yet. It's a fascinating idea, but without direct tests, it risks drifting into the realm of speculation. Still, there are faint hints that might eventually point the way. Some physicists suggest that if another universe ever collided with ours, like merging soap bubbles in a bath, it might have left detectable traces in the cosmic microwave background, the residual glow of the Big Bang. Others believe that subtle irregularities in high-energy physics experiments or anomalies in cosmic radiation could hint at interactions beyond our universe. To date, however, such evidence is inconclusive. The multiverse remains a concept teetering at the boundary between scientific theory, philosophical thought, and imagination. It dares us to confront fundamental questions about our existence. Are we merely inhabitants of one universe in a boundless multitude? Do other versions of ourselves exist, leading different lives in parallel realities? Or is the multiverse an illusion, a beautiful, intricate idea with no basis in physical reality? At present, we simply don't know. Yet the question persists. Our universe feels immense, ancient, and astonishingly complex. And still, it may be only a single note in a much grander cosmic composition, playing out across uncountable dimensions and infinite possibilities. The truth about the multiverse remains just out of reach, hidden beyond the furthest horizon of our knowledge. Whether it is a scientific breakthrough, a philosophical inquiry, or a bold stretch of the imagination, one thing is clear. The multiverse hypothesis forces us to reconsider everything we believed we understood about reality, about existence, and about our place in the cosmos. The arrow of time. The directionality of time, known as the arrow of time, remains one of the most profound unresolved questions in modern physics. According to the fundamental laws of physics, time does not inherently favor one direction over another. So why does time appear to consistently advance forward? A glass falls and shatters, scattering fragments across the floor, but those shards never spontaneously reassemble into a whole. On the microscopic scale, the universe shows no clear bias toward forward or backward motion. The equations that describe how particles interact and how forces behave are symmetric with respect to time. An electron, for instance, is indifferent to its movement. It behaves identically whether it's traveling into the future or reversing into the past. Yet, in our everyday experience, we constantly move forward in time, never backward. Why is that? This puzzle has perplexed physicists for centuries. One of those intrigued by it was Rudolf Clausius, a 19th century physicist who developed the concept of entropy, a measure of disorder within a system. Take a cold glass of water. Its molecules are ordered and calm, representing low entropy. Now pour in hot water. The warmth spreads evenly, increasing the system's disorder, resulting in high entropy. Clausius discovered that in any closed system, entropy will always increase over time. This insight led to the second law of thermodynamics, which stands as one of the most robust laws in all of science. Clausius recognized that this progression, from order to disorder, defined the arrow of time itself. Picture a flawless cup of coffee, black and still. Now pour cream into it. Initially, the cream swirls in graceful, white tendrils, creating elegant, dynamic patterns. But in time, those structures dissolve into a smooth, consistent brown. The system has transitioned from a state of lower entropy to higher entropy. There is no undoing it. Here's the unsettling implication. If entropy has always been increasing, it must have started at a remarkably low value. In the immediate aftermath of the Big Bang, the universe was astonishingly well ordered, a state of near-perfect balance. But why? Why would the cosmos begin in such an extraordinarily structured condition? Why not emerge in chaos? This question deepens the mystery. Some scientists propose that the universe naturally produces entropy as it expands. As more space emerges, new regions are created where disorder can grow, like ink spreading outward on an unending sheet. While this might explain why entropy increases after the Big Bang, it doesn't resolve the initial condition. Why did entropy start out so low? Other thinkers, such as physicist Julian Barber, have taken the debate further, suggesting a radical possibility. Time itself may not be real. Barber envisions reality as timeless, a series of fixed, unmoving instances, each representing a frozen moment in existence, like individual snapshots on an infinite film strip. While we perceive them as unfolding sequentially, they all exist at once, past, present, and future eternally coexisting in a unified tableau. If this view is accurate, then time, the forward arrow we cling to, could be nothing more than an illusion, a byproduct of our perception. Then there's the multiverse hypothesis. What if our universe is only one bubble among countless others in a vast cosmic expanse? In many of these universes, entropy may have begun in a much higher state, or time may not flow at all. Perhaps ours is a statistical outlier, a rare instance where low entropy happened by chance in a universe capable of developing time as we know it. Yet these explanations feel elusive, like distant echoes in the dark, slipping away as we try to grasp them. Every theory offers a glimpse of understanding, but none present a complete answer. Entropy continues its steady march. Stars blaze and die. Galaxies collide. And one day, entropy will prevail completely. The universe will exhaust all possible arrangements. Stars will extinguish. Black holes will evaporate. And all that remains will be a cold, quiet expanse, a lifeless equilibrium. Physicists call this the heat death of the universe. Time won't end because something broke, but because nothing will change. No distinction will remain between yesterday and tomorrow. No events will occur. Nothing will ever happen again. Fortunately, that fate is billions of years away. For now, the broken glass remains broken. The cream still spirals into the coffee, and tomorrow continues to await us, just out of reach. Time keeps moving forward, sweeping us along with it. A vast cosmic current flowing from the improbable structure of the past toward the growing chaos of the future. The arrow of time stands as one of the universe's most profound and disquieting enigmas. And yet, perhaps, hidden within the mathematics of entropy, the frozen frames of timeless existence, or the unpredictable outcomes of the multiverse, lies the elusive answer: the holographic principle. Take a moment to consider an extraordinary possibility: that everything you've ever known, from stars and galaxies to planets and even yourself, may not be what it appears to be. The universe, in all its vastness and complexity, might not actually be a true three-dimensional realm extending infinitely in all directions. Instead, it could be something entirely different, something flat, a two-dimensional surface where all of reality is merely projected, as if light were being cast through film onto a movie screen. This isn't a scene from a science fiction story. It's a real scientific concept known as the holographic principle, one of the most revolutionary and intellectually challenging ideas ever introduced in theoretical physics. This principle resides at the crossroads of black hole physics, string theory, and the nature of space and time itself. And it all stems from a puzzling realization about how information behaves and how black holes respond to it. But let's not jump ahead too quickly. To grasp how physicists arrived at this idea, we have to begin at the event horizon of a black hole. In 1974, physicist Stephen Hawking made a pivotal discovery. Black holes aren't completely black. They emit a faint type of energy now referred to as Hawking radiation. Over immense spans of time, this radiation causes black holes to lose mass and, eventually, to disappear entirely. However, this discovery introduced a serious contradiction. If a black hole vanishes, what becomes of the information it once held? In physics, one fundamental principle holds that information is never truly lost. If you incinerate a book, for example, its pages may become ash, and its ink may evaporate, but the precise details of its contents, in theory, still exist, dispersed in the smoke, heat, and particles. With enough knowledge and computational ability, that information could be recovered. This concept is central to physical law, yet Hawking's results seem to suggest that information swallowed by a black hole would be erased forever. This dilemma came to be known as the black hole information paradox, and it perplexed physicists for many years. One of those physicists was Gerard 't Hooft, a Dutch theoretical physicist who would later be awarded the Nobel Prize. In the 1990s, 't Hooft proposed a bold solution. Maybe the information that enters a black hole doesn't disappear at all. Instead, perhaps it gets preserved on the event horizon, the boundary surrounding the black hole. Picture a three-dimensional object falling into a black hole. According to this idea, the object's information doesn't vanish into the singularity. Rather, it's recorded on the surface of the horizon like a shadow cast onto a screen. This insight had immense implications. It suggested that everything occurring inside the black hole could, in theory, be fully represented by information encoded on its outer shell, a two-dimensional surface. But what if this logic didn't apply only to black holes? What if it extended to the entire universe? That's where Leonard Susskind, another prominent theoretical physicist, expanded upon 't Hooft's idea. Susskind proposed that the universe itself might follow a similar rule. All the activity we perceive within three-dimensional space could actually be described by data stored on a distant, two-dimensional surface, a sort of cosmic horizon enclosing everything within the observable universe. Put differently, our entire reality might be a hologram. Now, before spiraling into existential uncertainty, let's clarify. The holographic principle doesn't argue that the universe is fake or imaginary, like a simulation. Instead, it suggests that the deepest structure of reality could be far simpler than it appears, that the complex, three-dimensional cosmos might ultimately be defined by data imprinted on a two-dimensional backdrop. But how could that be possible? How can two dimensions fully describe a three-dimensional world? Consider how a hologram works. On a flat surface, a two-dimensional plane, you can encode patterns that, when illuminated, project the illusion of a full three-dimensional image. Walk around it, and you see depth, movement, and form. The 3D image doesn't reside in the sheet, it's projected from it. Similarly, the holographic principle posits that our perception of space, our experience of depth, distance, and motion may emerge from a deeper, flat structure beneath it. At this stage, the principle becomes much more than a theoretical curiosity. It transforms into a powerful mathematical tool. In 1997, physicist Juan Maldacena introduced a revolutionary theory called the AD/CFT correspondence. This theory offered a real-world model of the holographic principle, demonstrating that a universe governed by gravity in three dimensions could be mathematically equivalent to a universe governed by quantum mechanics in only two dimensions. In essence, gravity and quantum theory, once seen as irreconcilable, may be dual aspects of the same underlying reality, viewed through a holographic lens. This breakthrough rocked the foundations of theoretical physics. Suddenly, the holographic principle wasn't just a speculative idea. It was a concrete approach for bridging the gap between Einstein's general relativity and quantum mechanics, the two fundamental frameworks that describe our universe. But the implications grow even stranger. If our universe really is holographic, it raises deep philosophical questions. What does it mean to exist in a cosmos where space and time may not be fundamental components? Where everything we sense, see, and interact with is, at its most basic level, information etched onto a far-off cosmic boundary? It leads to an unsettling reflection. If the universe is fundamentally two-dimensional, then space and time, the stage on which every moment and memory unfolds, might not be solid foundations. They could be emergent features, similar to how ripples on a lake obscure the deeper water below. At present, the holographic principle remains a theoretical framework, a clue that may help unlock a long-sought theory of everything. Yet scientists are already exploring ways to test it. For example, researchers at Fermilab's holometer experiment are investigating whether spacetime itself exhibits tiny, jitter-like fluctuations, evidence of a pixelated, holographic universe. Whether or not these efforts produce definitive proof, the holographic principle has already reshaped how we think about existence. It suggests that the boundary between dimensions, between geometry and information, is far more complex than we once believed. It reminds us that reality, no matter how familiar or concrete it seems, may still conceal mysteries so strange they rival the imagination of fiction. So the next time you gaze up into the night sky, filled with stars and galaxies spread across unfathomable distances, consider this. It's possible that everything you see is simply a projection, data shimmering on the edge of a deeper, hidden truth. The Pioneer Anomaly. Far beyond the orbit of the outer planets, drifting silently in the vast, cold emptiness where sunlight fades into perpetual blackness, two solitary spacecraft continue their journey, Pioneer 10 and Pioneer 11. Created by human ingenuity and launched aboard blazing rockets in the early 1970s. These probes were among humanity's earliest explorers to cross into the uncharted expanse of interstellar space. Their purpose was to investigate the farthest planets and to extend our curiosity beyond the familiar bounds of the solar system. But in the quiet, uneventful decades that followed their launch, something unexpected began to appear. Subtle patterns in the data revealed a faint anomaly, an almost unnoticeable pull, as if some unseen presence was gently tugging the spacecraft back toward the sun. This mysterious behavior came to be known as the Pioneer Anomaly, a baffling enigma that would perplex physicists for decades and challenge some of the most fundamental ideas about gravity. Pioneer 10 took flight in 1972, with Pioneer 11 following in 1973. Each carried with it a golden plaque inscribed with a symbolic greeting from Earth to whatever life might one day encounter it. The probes flew past Jupiter and Saturn, capturing astonishing images and gathering unprecedented data. Eventually, they traveled beyond the realm of the planets into the dark unknown, where the sun became little more than another star among billions. Initially, everything followed expectations. Scientists had plotted the spacecraft's paths with incredible precision, based on the known laws of physics. But as time passed, signals transmitted from the spacecraft began revealing a strange inconsistency. The probes were not exactly where they should have been. Both Pioneer 10 and 11 were moving ever so slightly slower than projected, as if a faint, invisible force was holding them back. Though minuscule, the change in speed, roughly 110 billionths of a meter per second squared, was enough to catch the attention of researchers. In space, where accuracy is everything, such a discrepancy couldn't be ignored. The effect was subtle, but it was consistent, persistent, and deeply puzzling. Initially, scientists turned a skeptical eye toward the data itself. Could there be a flaw in the instruments? A miscalculation in the trajectory models? But as new data was analyzed and reanalyzed, the anomaly held its ground. It refused to disappear. What had first seemed like a minor irregularity now stood as a challenge demanding explanation. Could it be a signal pointing toward unknown physics? Was an undiscovered force acting in the void? Or, perhaps even more unsettling, could our very understanding of gravity be incomplete? Theories began to circulate. Some scientists proposed that dark matter, the unseen substance thought to make up much of the universe's mass, might be influencing the probes. Others speculated about alternative models of gravity, slight alterations to Einstein's equations that could account for the unexpected behavior. Still more imagined far-fetched ideas: friction from interstellar particles, interference from hidden dimensions, or even quantum interactions with the fabric of spacetime itself. But before scientists could tear down established physics, they had to examine every mundane possibility. Could something ordinary like heat be to blame? After all, the Pioneer spacecraft were powered by radioactive generators, which continuously emitted heat. And in principle, that heat could create minuscule forces. If the thermal radiation was being released unevenly, it might produce a gentle, continuous push, small enough to go unnoticed, yet large enough to shift the probes over time. Though less thrilling than exotic physics, this explanation demanded thorough investigation. Science, after all, depends on meticulous evidence, not dramatic conclusions. Over the next several years, researchers pored over engineering data, dissected telemetry records, and constructed complex models to simulate how heat escaped from the spacecraft. They calculated the trajectory changes caused by each photon of thermal energy leaving the system. Slowly but surely, the pieces of the puzzle began to fit together. Ultimately, the cause of the anomaly emerged. Uneven thermal radiation from the rear of the spacecraft was generating a slight recoil force, like a gentle breath nudging the probe backward. It was an incredibly faint effect, but it was enough. By 2012, after years of scrutiny and debate, the mystery was largely settled. The anomaly was not the result of dark matter, exotic forces, or hidden spatial dimensions. It was caused by heat, ordinary, unglamorous heat. The universe had not violated its own laws after all. But this wasn't simply the end of a scientific riddle. Solving the Pioneer Anomaly was more than just an answer to a question. It was a demonstration of the scientific process itself. It showed that careful, systematic investigation, rooted in evidence and unshaken by speculation, could shed light even on mysteries that seem impossible. It reminded us that nature doesn't give up its truths easily, and that answers are often found not in grand theories, but in the smallest overlooked details. And yet, even though the anomaly was explained, the story of Pioneer 10 and Pioneer 11 still resonates. These quiet explorers continue their solitary voyage through space. Their transmitters have long fallen silent. Their systems are no longer active, but they remain, drifting through the stars, messengers from a distant blue world orbiting an average star, bearing the legacy of our curiosity and our need to explore. One day, perhaps in a future so distant we cannot imagine it, another civilization might intercept one of these ancient probes. They might discover the golden plaque, etched with diagrams of a man and a woman, and wonder about the beings who created and launched these fragile machines into the darkness. They might even ponder what motivated a species to send such delicate craft into the cold, black void. The Pioneer Anomaly began as a question about physics, but it ended as something more, a reflection on the human drive to explore, to question, and to understand. It serves as a reminder that every mystery we solve brings us closer to the heart of reality, and that every solution, in turn, opens the door to new questions. The journey of the Pioneer probes isn't only a tale of space science. It is a story of humanity's relentless curiosity. And as these spacecraft continue to glide silently through the cosmos, they remind us of a profound truth. The universe is vast, full of wonder, and always waiting for the next question to be asked. The nature of dark flow. The universe, immense and unrelenting, extends far beyond our sight, an infinite sea of stars and emptiness. Its immensity challenges our ability to grasp it, its secrets buried deep within cosmic darkness. And still, amid all the knowledge we've gained, one elusive signal continues to echo, a subtle yet persistent force, like a hidden current pulling entire galaxy clusters steadily in a single direction. This strange and unexplained movement is called dark flow, and it questions not only our grasp of gravitational forces, but also the underlying nature of existence. Across the vast design of the cosmos, galaxies do not float without order. They move, drift, and fall toward gravitational basins, shaped by the unseen structure of dark matter and other massive cosmic formations. Most of this cosmic motion can be interpreted through what we understand as the expansion of the universe, an outward spread driven by dark energy. Yet in 2008, researchers analyzing findings from NASA's Wilkinson Microwave Anisotropic Probe WMAP noticed something surprising: a slight, yet measurable, directional drift of galaxy clusters, moving together like debris swept along by a powerful river current. This pattern wasn't predicted by existing cosmological theories. According to the most widely accepted models, galaxy clusters on such scales should appear randomly scattered, their movements influenced only by local gravitational effects and the universal expansion of space. But the observations suggested a more significant influence at work, one capable of steering entire regions of the observable universe toward some unknown endpoint. The implication sent shockwaves through the scientific world. If dark flow was real, it implied the presence of something enormous lurking beyond what we can observe, something we can't see or detect directly, but which still manages to exert a powerful influence. Picture yourself at the edge of a limitless sea, watching the waves not being pushed by the wind, but pulled toward a distant point beyond your sight. You can't perceive the cause directly, But the motion proves something immense must lie out there, hidden, but undeniably real. So how did scientists manage to detect such a faint movement across unimaginable distances, where countless cosmic forces interact? They relied on what is known as the Sunyaev-Zeldovich effect, a delicate distortion of the cosmic microwave background radiation, caused by the interaction between this ancient light and the superheated gas within galaxy clusters. By carefully measuring these minor variations, astronomers were able to estimate the motion of clusters relative to the lingering afterglow of the Big Bang. The results were striking. Clusters of galaxies, spread across billions of light years, appeared to be moving together, traveling at speeds reaching up to 1,000 kilometers per second. The directionality and scale of this flow were too pronounced to be dismissed as chance or observational mistake. It pointed to a massive, external source of gravitational influence, something located beyond the limits of what we can currently observe. Speculations soon emerged. Some theorists suggested that the cause could be a massive formation lying past the observable boundary, perhaps an enormous supercluster, or a relic of an earlier universe merging with ours. Others proposed that gravity itself might be leaking into our universe from extra dimensions, beyond the four we experience daily. And then came the most astonishing possibility of all, that dark flow might be a sign of a multiverse, that our universe could be brushing against another, hidden beyond the cosmic horizon, causing this unexplained gravitational effect. But the mystery deepened further. Our understanding of the universe includes a limit, known as the cosmic horizon, beyond which light has not had time to reach us since the birth of the cosmos. Everything beyond that point lies beyond observation. Still, dark flow suggests this edge may not be the boundary of existence, only the edge of what we can perceive. This leads to profound questions. Are we feeling the faint gravitational influence of a structure far outside our cosmic reach? Could our universe be just a single droplet in an endless expanse, each droplet affecting the next through forces we cannot yet detect? And if that's true, what does that say about our place in all of this? Are we not stationary observers, but rather passengers aboard a drifting vessel, pulled by unseen currents toward an unknowable destination? Not all scientists agree on the existence of dark flow. Later measurements, such as those from the Planck satellite, cast doubt on its strength. Some researchers suggest that the phenomenon might be an illusion, caused by statistical irregularities or biases in the way the data was interpreted. Still, others are convinced that the movement is genuine, even if we have not yet identified its cause. But perhaps the most important aspect of dark flow is not whether it is real or an error, but what it represents. If it does exist, it challenges the idea that our universe is a sealed system, a closed shell of galaxies drifting quietly into an empty void. Instead, it implies that we are connected by invisible threads to something far greater, something older and larger than our universe, something beyond understanding. Think about this. Every galaxy, every star, every world, including our own, is a part of this massive motion. We are not simply watching the cosmos from a fixed position. We are caught in a vast cosmic current, moving along with forces that predate everything we know, toward a destination that lies outside the reach of light and knowledge. And maybe, just maybe, we will never uncover the source. Perhaps the origin of dark flow will always remain cloaked beyond the cosmic edge. Or perhaps future instruments, revolutionary ideas, and bold new investigations will allow us to see just a bit farther, offering a glimpse of what lies beyond. Until that moment, dark flow remains an open question, a phenomenon veiled in gravity, cloaked in cosmic darkness, and imprinted in the silent motion of galaxies across incomprehensible distances. It stands as a symbol of how much we still have to learn, of how small we truly are, and yet how deeply woven we are into the universe, into each other, and into the great unknown that stretches beyond the edge of what we can see. In the end, dark flow is more than a movement of galaxies. It reflects the invisible pull we all feel toward the unfamiliar, the mysterious, and the unsolved. It speaks to the essence of the human spirit, to reach beyond the horizon, to seek, to question, and to follow even the faintest hints left behind by the universe. So we continue to drift, all of us, bound by invisible forces, carried through the unknown, and somewhere beyond the final edge of light, the universe remains silent and waits. The constants of nature. Nature often appears to run with flawless precision. Stars ignite, planets revolve, and atoms oscillate in ways we can predict, each motion following rules set by fundamental constants. These constants are universal figures, woven into the essence of existence itself: the speed at which light travels, the strength of gravity, the electrical charge of an electron. They form the very backbone upon which the universe constructs its complexity. But what if these constants are not truly fixed? It's a question that sounds almost rebellious. After all, the structure of the cosmos depends on these values remaining steady. Even a slight alteration in the gravitational constant could stop stars from forming, prevent galaxies from coming together, and eliminate the possibility of life altogether. The entire cosmic order could fall into disarray. Still, some theoretical physicists propose that these constants might not be as unchanging as we believe. At the center of this idea lies one of the most peculiar hypothetical particles ever suggested, the axion. The axion was originally introduced to resolve a puzzle within quantum chromodynamics, the field that explains how quarks interact through the strong nuclear force. According to the mathematics of the theory, this force should violate a rule known as CP symmetry, which means that if all particles were swapped with their antiparticles and the universe was mirrored, the laws of physics should stay exactly the same. But oddly, the strong force does not appear to break this symmetry at all. It behaves with an eerie precision that the theory cannot explain. This inconsistency is referred to as the strong CP problem, and the axion was imagined as a theoretical solution meant to restore balance to the equations. Yet, as is often the case in physics, the axion turned out to be far more than a convenient fix. If actions exist, they may not only resolve issues within the strong nuclear force, they could also help solve one of the greatest mysteries in cosmology: dark matter. Due to their ethereal characteristics and their extremely weak interactions with ordinary matter, actions are among the leading candidates for this unseen mass that binds galaxies together. But the implications of the axion go even deeper. In some advanced theoretical frameworks, actions might behave like cosmic tuning knobs, subtly adjusting values like the fine structure constant, which controls how light interacts with charged particles. If actions are capable of varying over time and space, then the so-called constants of nature may not be fixed at all. Astronomers have already begun seeking signs of such cosmic variability. They examine light from quasars, ancient beams that have crossed vast stretches of space and time. If the fine structure constant had a slightly different value billions of years ago, that difference would be imprinted within the makeup of this ancient light. And in some observations, faint clues have appeared, slight shifts, inconsistencies that resist easy explanation. However, the evidence remains inconclusive. The search for actions continues, deep underground in highly shielded laboratories, where magnetic fields and ultra-sensitive instruments are employed to catch even the faintest hint of these ghost-like particles. Each experiment pushes the boundaries of what we can detect, drawing us a little closer to the truth. Yet the axiom still lies just out of reach, a shadow at the edge of our comprehension. If discovered, actions wouldn't simply plug holes in existing theories of matter and the universe. They would upend one of our deepest assumptions, that the universe operates on a foundation of eternal, immutable constants. Instead, they could reveal that these constants are not fixed values at all, but fluid characteristics molded by the evolving cosmos. For now, the investigation stretches onward, through the ancient light of distant galaxies, within powerful magnetic chambers, and across the mathematical landscapes of theory. The axiom stands as one of the most captivating possibilities in contemporary physics. And with every piece of new data, with each curious signal that defies expectation, we edge closer toward either confirming the existence of this elusive particle or redefining the very principles we believe the universe to be built upon. Dark matter and dark energy. Across the immense reaches of the cosmos, amid a glittering sea of stars and spiraling galaxies, an unseen presence looms, an invisible force that holds dominion over the universe. It emits no light, casts no reflection, and doesn't engage with matter in any known way. Yet without it, the galaxies would disband, stars would scatter into deep space, and the structure of the cosmos would fall into disarray. This enigmatic force is known as dark matter, and as baffling as that is, something even more puzzling lurks in the cosmic void, a strange energy that drives galaxies apart, stretching reality itself. We've come to call it dark energy. Together, dark matter and dark energy comprise more than 95% of the entire universe. Everything visible, stars, planets, nebulae, even all the atoms and photons, makes up less than 5%. The remainder is composed of unseen forces, not the comforting darkness of night, but a deeper, unknowable mystery built into the fabric of space and time. The tale of dark matter began nearly 100 years ago, when astronomer Fritz Zwicky investigated a galaxy cluster known as the Coma Cluster in the 1930s. Using Newton's laws, he attempted to calculate how fast these galaxies should be moving, based solely on what they could detect: stars, gas, and other observable matter. But something was wrong. The galaxies moved far faster than expected. So fast, in fact, that they should have flung themselves apart, drifting into emptiness. Yet they didn't. Instead, they remained bound together, held in place by some invisible gravitational force. To account for this, Zwicky proposed the existence of dunkel materie, dark matter, a substance that couldn't be seen but whose gravitational effect kept the galaxies intact. At first, many doubted his conclusion, but years later, astronomer Vera Rubin uncovered compelling support. While studying how spiral galaxies rotate, Rubin made a startling observation. According to Newtonian mechanics, stars further from the galactic center should orbit more slowly, just as outer planets move more slowly in our solar system. But this wasn't the case. Instead, stars at the outer edges of galaxies moved just as quickly as those near the core, defying conventional physics. The only reasonable explanation was that galaxies were surrounded by a massive, unseen halo, dark matter exerting gravitational force well beyond the reach of visible stars. Still, the exact nature of dark matter remains elusive. Though its presence is inferred from its effects, it doesn't emit, absorb, or reflect light, nor does it interact with ordinary matter in any direct way. Scientists theorize that it may be composed of exotic, undiscovered particles, such as WIMP's weakly interacting massive particles or actions, both hypothetical particles that engage only through gravity or the weak nuclear force. Around the world, physicists conduct experiments in underground laboratories and high-energy colliders, hoping to detect a sign of this invisible component. But for now, dark matter remains a phantom, an unseen player influencing the dance of galaxies. And yet the cosmic mystery deepens even further. If dark matter acts as the hidden framework holding the cosmos together, then dark energy is its opposite, a repulsive force that drives everything apart. In the late 1990s, two separate groups of astronomers observing distant Type Ia supernovae made a shocking discovery. They had expected the expansion of the universe to be slowing down as gravity pulled galaxies back toward one another. But what they found defied expectations. The universe's expansion was speeding up. A force was working against gravity on the largest scales, flinging galaxies outward faster and faster. That repelling force was named dark energy. It's estimated to comprise roughly 70% of all energy in the universe. The realization overturned existing models of cosmology and left scientists grappling with a haunting question. What is dark energy? Exactly. One possible answer involves vacuum energy, a property of empty space itself. According to quantum physics, even the emptiest vacuum is never truly empty. Instead, it's a roiling field of fleeting virtual particles, constantly forming and vanishing. This energy, though minuscule, might accumulate across the enormity of space to produce a push, a cosmic pressure driving galaxies apart. Another explanation revisits Einstein's cosmological constant, a term he originally inserted into his equations of general relativity to achieve a static universe, only to later abandon it as a mistake. However, with the discovery of the accelerating universe, this constant suddenly gained renewed relevance, possibly representing dark energy. But attempts to calculate its value using quantum field theory result in a number that's 120 orders of magnitude too large, a staggering mismatch known as the vacuum catastrophe. Among the most glaring contradictions in modern science, some theorists propose that dark energy might not be constant at all, but instead a changing, evolving force, something they refer to as quintessence. Unlike the cosmological constant, quintessence would evolve over time, subtly altering the future trajectory of the universe. But so far, this remains speculative, a possible whisper in the dark. Together, dark matter and dark energy compose a portrait of a universe that is both stunningly beautiful and profoundly foreign. They reveal how much remains beyond our reach, how deeply the cosmos resists simple explanation, and yet we can observe their influence. We witness dark matter in the clustering of galaxies. We detect dark energy through the redshift of distant starlight, a sign of space itself expanding. Though unseen, these forces mold the universe. They dictate how galaxies form, how matter clumps, and how the future unfolds. And the journey to understand them continues. Physicists operate detectors in shielded labs, hoping to register a dark matter particle's passage. Astronomers scan deep space for subtle signs of dark energy hiding in ancient light. Ultimately, dark matter and dark energy confront us with a sobering truth. Most of the universe lies hidden beyond the reach of our senses, buried in realms we're only starting to explore. Yet the most profound question may not be what these forces are, but why they exist at all. Why is the universe built upon such delicate balance? A cosmic push and pull between unseen forces that bind it together and others that rip it apart. Perhaps the answers lie in the quiet tremor of gravitational waves, in the flicker of ancient starlight, or in the silence of a particle detector waiting far below the Earth's surface. Or perhaps, for now, the cosmos will keep its secrets a little longer. We're left with a universe dominated by the unseen, a realm sculpted by shadows and defined by what we cannot observe, but must still understand. And in those shadows, wrapped in layers of cosmic mystery, may rest the key to understanding not only the universe, but also our place within it. Out in the stillness of deep space, amidst the slow dance of galaxies and the endless stretch of the void, the universe remains poised, and in the soft glow of distant stars and the whisper of fading quasars, the truth awaits our discovery. The heat death of the universe. At present, the cosmos seems full of life. Stars blaze intensely, planets trace stable orbits, and galaxies sweep majestically through the fabric of space in vast, elegant spirals. From subatomic particles to supermassive black holes, energy circulates, motion continues, and time steadily progresses. But eventually, all of this will cease. Every star will extinguish, every galaxy will grow frigid, and every form of motion or glimmer of energy will disappear into utter stillness. This is what we call the heat death of the universe, a chilling portrayal of the universe's final state, a reality in which nothing occurs, nothing transforms, and nothing ever will again. But how can such a destiny come to be? How does a universe brimming with brilliant stars and dynamic galaxies slowly fade into a frozen stillness with no end? To understand this, we must explore the idea of entropy. In the mid-1800s, scientists such as Rudolf Clausius and Ludwig Boltzmann introduced the concept of entropy, a measurement of disorder within a physical system. Consider a mug of hot coffee placed in a chilly room. As time passes, heat from the coffee disperses into the air. Eventually, both the coffee and the room reach the same temperature, and the transfer of heat stops. The system has arrived at thermal equilibrium. This same principle applies to the universe. Energy naturally flows from concentrated to dispersed areas, from high temperature to low, from structured to chaotic. And with every transfer of energy, a portion becomes inaccessible, trapped in forms that can no longer perform work. This fundamental principle is known as the second law of thermodynamics, one of the core laws of physics. In any isolated system, entropy will always increase over time. And since the universe is the ultimate isolated system, this rule applies to everything. Currently, our universe is in a state of remarkable activity. Stars are fusing hydrogen into helium, emitting vast amounts of energy. Planets soak up starlight. Black holes devour matter. Energy shifts continuously, powering the cosmic ballet and illuminating the heavens. But this won't continue indefinitely. Stars are not immortal. Roughly 100 trillion years from now, the final stars will exhaust their fuel. These last stars will be red dwarfs, small, dim, and slow-burning stars that take an enormous amount of time to consume their hydrogen. But even these enduring beacons will one day go dark. When the last flicker of stellar light fades, the universe will enter a new phase, the degenerate era. This era will be ruled by the remnants of dead stars, white dwarfs, neutron stars, and black holes. These are stellar leftovers, cosmic corpses. They do not radiate light, do not initiate new creation. They simply persist in a cold, inactive state. However, not even these will last forever. Over timescales that boggle the mind, white dwarfs will gradually release their heat and become black dwarfs, solid, icy orbs composed of carbon and oxygen, drifting silently through the void. Meanwhile, black holes will begin to vanish through a process called Hawking radiation. In the 1970s, physicist Stephen Hawking showed that black holes are not truly black. They emit tiny amounts of radiation and slowly lose mass. Given enough time, spanning -0 to the power 1 years or more. Every black hole in the universe will eventually evaporate completely, disappearing into nothing. What remains after this final vanishing? Only the most elementary particles, protons, electrons, neutrinos, floating through an immense, dark, and nearly empty expanse. Yet even these may not be permanent. Some scientific models suggest that protons may decay after an unfathomable length of time, leaving behind only faint radiation and low-energy light. The universe will be devoid of stars, planets, and even black holes, just a sparse, cold haze of subatomic particles dispersed across a boundless emptiness. At this point, the cosmos will have reached maximum entropy. All usable energy will have been evenly spread throughout space. There will be no contrasts, no heat differences, no flows of energy, no conditions for life, complexity, or structure. Time itself will lose all relevance, for time, as we perceive it, is rooted in change. In a universe where nothing changes, does time still hold meaning? This is the essence of heat death, a universe where everything has settled into final, irreversible stillness. Yet despite its somber tone, there is a kind of stark beauty in this vision. For eons, stars illuminated the skies, galaxies twirled in graceful patterns, and life, ephemeral and fragile, emerged to observe it all. The universe became a grand stage, and for a fleeting instant, it was filled with brilliance, motion, and wonder. But nothing endures forever. Perhaps in some quiet corner of this cooling universe, there will be one last photon, escaping from the decay of the final particle, gliding through infinite night, bearing the final remnant of a universe that once teemed with light and vitality. The heat death of the universe will not be marked by cataclysm or spectacle. There will be no massive explosion, no apocalyptic crescendo. It will be a slow, methodical dimming, a long, cold fade into silence. The story of everything began with a bang. It will conclude with a whisper, a soft, eternal exhale stretched across the endless canvas of time. Quantum tunneling. At the foundation of existence lies a cosmic rulebook, a collection of basic principles that govern the workings of the universe. These principles are constant, dependable, and in most cases, predictable. Drop an object, and it will descend. Warmth naturally moves from hot regions to cooler ones. A solid wall halts your motion. Yet beneath this apparently consistent surface, in the strange world of quantum physics, the laws begin to behave oddly. Here, particles defy our everyday expectations. They fluctuate, shift, and at times, they do something utterly bizarre. They slip through obstacles as though the barriers were never there. This remarkable occurrence is known as quantum tunneling, one of the most puzzling features in all of physics. Imagine yourself standing before an immense mountain. You could devote a lifetime trying to scale it or burrow underneath. In the conventional, macroscopic world guided by Newtonian mechanics, walking straight through the mountain would be unthinkable. But in the weird realm of quantum behavior, tiny particles, such as electrons and protons, and even full atoms, have been observed doing exactly that. How can this happen? And more curiously, are there limits to this quantum strangeness? To grasp tunneling, we need to examine how particles act on a quantum level. In our everyday world, particles are treated as solid, definite things. A marble on a tabletop is either in one place or another. But in quantum mechanics, particles behave both as discrete particles and as waves, a paradoxical quality that challenges logic. Instead of having one clear position, A quantum particle is described by a probability wave, a mathematical cloud representing where it might be found. Picture tossing a pebble into still water. The waves it creates ripple outward in all directions. Similarly, a quantum particle's wave function spreads throughout space, indicating the chances of discovering it in different spots. Now, place a wall in the path of those waves. In classical terms, the waves would be halted. But in quantum physics, the wave function doesn't completely stop. It seeps through. On the far side of the wall, a faint wave remains, meaning there's still a tiny chance the particle might appear beyond the barrier, where it logically shouldn't be. This isn't merely theoretical speculation. Quantum tunneling is crucial to many of the universe's core mechanisms. Within the hearts of stars, hydrogen atoms are able to fuse by overcoming the repelling forces between their positively charged nuclei. Normally, such fusion would be nearly impossible due to this repulsion, but tunneling allows them to sneak through energy barriers, producing the light and heat that stars emit. On Earth, tunneling has enabled groundbreaking technologies. Scanning tunneling microscopes allow scientists to observe individual atoms by harnessing the tunneling behavior of electrons. Tunneling is also fundamental in technologies like flash memory, where electrons tunnel through insulating materials to store digital data in devices like smartphones and computers. Yet, as amazing as quantum tunneling is, it doesn't come without limitations. For a particle to tunnel, the obstacle can't be excessively wide or impossibly tall. There must be at least a slight chance for the particle to make it to the opposite side. As the size or height of the barrier increases, the probability of success drops dramatically. Tunneling is not a shortcut around reality. It's more like gambling with impossible odds and hoping to win. Still, physicists continue to push the boundaries of what's possible. In labs across the globe, scientists have succeeded in tunneling entire molecules and even clusters of atoms, challenging what we thought were the outer limits of this phenomenon. But what about something bigger? A virus? A human cell? An actual person? In theory, such a thing is possible. In practice, it is almost certainly unachievable. The quantum wave function for something as complex as a human body is extraordinarily small. The odds of every atom in your body coordinating to tunnel together at once are so vanishingly tiny that it's virtually impossible. Less likely than spelling out the entire script of Hamlet by tossing Scrabble tiles into the air. Even on microscopic scales, tunneling remains deeply mysterious. Recently, researchers have been investigating how long tunneling takes. Is it instantaneous? Or does the particle cross the barrier in steps? Experiments using ultra-fast lasers suggest the process might occur much faster than we thought, potentially even instantly. But this puzzle remains unsolved, lying just beyond our current comprehension. And then there's a bigger question. Could tunneling be telling us something deeper about the structure of reality? Might it point to hidden dimensions or offer clues about new physics beyond our present models? Some scientists think tunneling could provide insight into the elusive theory of everything, a unified framework that merges quantum physics, gravity, and the entire universe into one seamless equation. At its essence, quantum tunneling is a testament to the uncanny and wondrous nature of the cosmos. It reveals that, on the smallest scales, reality isn't firm or consistent. It's uncertain, statistical, and fundamentally enigmatic. Particles don't observe the boundaries we expect. They blur distinctions between presence and absence, between what exists and what doesn't. So the next time you gaze at starlight or save a picture on your phone, remember this. Deep in the underlying fabric of the universe, particles are bending the rules. They're slipping past obstacles, ignoring the ordinary, and proving that our reality is stranger and more astonishing than we ever dreamed. And maybe, just maybe, hidden somewhere within the extremes of quantum tunneling lies the key to the next revolutionary insight in our understanding of existence. The real question isn't whether something will pass through that ultimate barrier. It's only a matter of when. The rise of consciousness. Within the immense tapestry of the cosmos, crafted from particles, interactions, and elemental rules, there exists a phenomenon so perplexing, so hard to pin down, that it seems to sit beyond the reach of the physical sciences. Consciousness. Right now, you're immersed in it. The quiet current of your thoughts, the sudden spark as you interpret these lines, the unmistakable awareness of your own being. This experience feels more concrete than the physical molecules that form your body. Yet, this leads to a profound conundrum. How does consciousness originate from non-living matter? How does it arise from basic particles like electrons and quarks, through the machinery of chemistry and biology? To explore this, we must travel from the minuscule dynamics of subatomic particles, through the immense complexity of the human brain, and into the philosophical depths that challenge the essence of existence. Physics has given us remarkable insight into the workings of the universe, from nuclear fusion lighting up stars to quantum entanglement linking particles across astronomical distances. But can it also explain the inner experience of being alive? Consciousness, at its heart, feels indivisible. A star can be reduced to a mix of helium and hydrogen, a living cell broken down into proteins and strands of DNA. But how do you dissect a memory, an emotion, the redness of red, the flavor of sugar, the grip of fear or pain? This riddle is what philosopher David Chalmers labeled the hard problem of consciousness. It's not about mapping brain regions or explaining neurological pathways. Those are the so-called easy problems. Odd as it sounds, the hard problem asks, why do these biological functions produce subjective experience at all? Why does the universe not exist as a purely mechanical system, devoid of inner life? Science has made impressive strides in tackling the easy problems. Brain science can chart neural circuits, trace impulses, and interpret how neurons fire. But despite this progress, there is still no answer for how electrical signals in the brain generate conscious awareness. It's as if we've diagrammed every component in a television and tracked every wire, yet still can't understand why the screen displays a picture rather than just lighting up circuits. Some theorists believe that unraveling consciousness may require a fundamental rethinking of what reality itself is. One such idea, integrated information theory, suggests that consciousness emerges wherever information is deeply and meaningfully interconnected, such as within the brain. Another idea, orchestrated objective reduction, proposes that quantum-level activity within neurons might give rise to consciousness itself. This concept implies that consciousness might stem from the strange behaviors of the quantum world, where conventional logic doesn't always apply. But this only deepens the mystery. Is consciousness a byproduct, like how wetness appears when hydrogen and oxygen form water? Or is it something fundamental, something built into the structure of reality, like gravity or time? Some thinkers propose that consciousness might be a basic feature of the universe itself. In this framework, every particle might carry a glimmer of awareness, a minimal element of experience. This view, called panpsychism, may seem far-fetched, but it is gaining interest among respected scientists and philosophers. Let's pause and consider a scenario. Picture an artificial brain, an exact, functional duplicate of your own, with every neuron replicated and every signal mirrored perfectly. Would such a synthetic mind have conscious experiences? Could it feel joy, sorrow, or curiosity? Or would it simply behave as if it were alive, a philosophical zombie, mimicking awareness, but lacking real sentience? If your answer is no, that this artificial entity would not truly be conscious, then perhaps something crucial about the origins of consciousness is still missing. There's also an idea that consciousness and physics might be tightly linked at the quantum scale. Some scientists propose that quantum entanglement, where particles remain mysteriously bound even over great distances, could resemble how different brain regions coordinate to create a unified sense of self. Could it be that consciousness is a form of quantum entanglement, playing out in biological systems? It's an intriguing theory, but one that remains purely speculative. On the other end of the spectrum is a disquieting alternative. What if consciousness is merely an illusion? A mental trick evolved to help us survive, a construct with no actual depth behind it. In this view, your thoughts, emotions, and sense of self are simply neural noise, a convincing light show generated by a biological system. Some scientists argue that consciousness may not require an explanation at all, that it's something to move past, like a mirage shimmering over desert asphalt. Yet even so, you're still here, feeling, observing, existing. No matter what theory you consider, consciousness remains undeniably real to the one experiencing it. And that's the contradiction. Consciousness is at once the most personal and the most puzzling feature of existence. To grasp it fully, we may need more than physics or neuroscience. We may need to unite these fields with philosophy, artificial intelligence, or other disciplines we've yet to invent. Maybe the answer lies hidden within a new natural principle, something as revolutionary as general relativity or quantum theory. Or maybe the question is beyond our reach entirely, that the truth about consciousness is locked behind a door we'll never open. But one thing is beyond doubt. Understanding consciousness is not just about solving a puzzle. It's about confronting the mystery of who we are, our role in the cosmos, and the very shape of existence itself. Whether it turns out to be an emergent feature, a quantum structure, or a core part of the universe's fabric, consciousness remains the greatest puzzle in science, a reflective surface not only showing us the universe, but also revealing the deepest questions about what it means to exist. So we leave this question suspended in thought, as countless minds have done before us. What is consciousness? Is it a deception crafted by biology? A divine flame hidden within us? Or the most essential ingredient of all reality? Maybe, just maybe, the answer already lives inside us, quietly waiting between the flicker of a neuron and the breath of a thought. The disappearance of cosmic lithium. After the Big Bang, the universe existed as an immense, turbulent sea of searing heat and density, protons, neutrons, and electrons moving chaotically, crashing into each other, merging and breaking apart in a primordial storm. This chaos marked the beginning of everything we recognize today. As this fiery landscape cooled, a remarkable phenomenon unfolded, a period known as Big Bang nucleosynthesis. Occurring mere minutes after time began, it was during this short interval that the universe gave birth to its first atomic building blocks: hydrogen, helium, and a faint trace of lithium. These light elements laid the groundwork for the formation of stars, galaxies, and ultimately, life as we know it. Yet, within this graceful tale of cosmic formation, something seems amiss. This brings us to a long-standing mystery: the cosmic lithium discrepancy, a conundrum that has resisted resolution for generations. Based on our most trusted calculations of the universe's infancy, there should be roughly 3 times as much lithium scattered through space as what telescopes actually detect. For reasons still unclear, this fragile element appears to have vanished, been obliterated, or perhaps never came into existence in the predicted quantities. This contradiction troubles the foundations of cosmological theory. It suggests either a flaw in our comprehension of nuclear processes or something even more mysterious hidden within the framework of the universe itself. To grasp this puzzle, we must revisit those opening minutes of the cosmos. Hydrogen, the simplest and most plentiful element, formed almost spontaneously. Helium emerged next, its creation governed by predictable and well-understood nuclear interactions. Lithium, however, the universe's third light element and the third entry on the periodic table, was far more difficult to produce. Its synthesis depended on a fine-tuned convergence of conditions, exact temperatures, precise pressures, and specific particle behaviors. Any small variation could easily throw off the delicate reaction chain required for lithium to form. Theoretical models estimate that for every 10 billion hydrogen atoms, one lithium atom should have been created. However, when astronomers examine ancient stars, stellar fossils that have remained relatively unchanged since the earliest epochs, they consistently detect only a third of the predicted lithium. It's as though 2/3 of the element has somehow disappeared. This puzzle has occupied scientists for decades. Some hypothesize that stars may have destroyed the lithium, consuming it in their blazing cores. Yet this theory falls short. Many of the stars studied are extremely old and relatively cool, conditions unlikely to erase that much lithium. Others argue that the lithium may have been diluted in the outer layers of stars, hidden from detection. But even with sophisticated instruments, astronomers struggle to bridge the gap between prediction and observation. In 2012, attention shifted toward more exotic ideas. Could unfamiliar particles, remnants from the earliest phases of the universe, have interfered with lithium formation? The concept of new physics, beyond the standard framework, started gaining ground. Some unknown influence that may have subtly disturbed the nucleosynthesis process. Some researchers even proposed that dark matter might be involved, altering the nuclear reactions in ways we don't yet understand. An even more intriguing possibility is that our very picture of the early universe is flawed. What if the process of Big Bang nucleosynthesis didn't unfold exactly as we believe? Could there have been a hidden phase transition, a transformative moment in the universe's infancy that rewrote the rules of elemental creation? These ideas are not wild guesses. They represent serious tensions within a scientific model that, otherwise, describes the cosmos with great success. But this isn't just ancient history. Lithium remains deeply important in the present day. It is crucial in modern electronics, essential for the rechargeable batteries that energize smartphones, laptops, and electric vehicles. More fascinatingly, lithium also influences the human mind. It is used in medicine, particularly in mood-stabilizing drugs that treat mental health disorders. It's striking to think that this small, silvery element, so important to both technology and biology, is also tied to a profound mystery about the universe's origin. And so, the enigma persists. Even with all the elegance and precision our science affords, the universe continues to guard its secrets. The lithium problem is more than just a missing metal. It represents a boundary in our knowledge, a subtle reminder that we don't yet have all the answers. The solution may lie in uncharted physics, awaiting discovery in high-energy particle collisions, or in the faint glow of far-off stars, waiting for the next generation of telescopes to decode it. For now, lithium remains an unsolved riddle in the vast cosmic puzzle. But perhaps that's what gives science its beauty, the unanswered questions, the gaps in our knowledge that invite us to search deeper. The cosmic lithium mystery is not just a scientific inconsistency. It's a gateway, a clue that somewhere, embedded in the architecture of reality, something extraordinary waits to be uncovered. And maybe, In the not-so-distant future, we'll find it. Black hole singularity. At the boundaries of our comprehension, where even light falters and fades, and the principles of physics fold under their own strain, there exists a limit. This threshold, both dreaded and admired in scientific circles, is known as the event horizon of a black hole. It acts as a cosmic divide, beyond which the familiar dissolves into the unknown. But what lies on the other side? What unfolds at the very center of a black hole? The answer, or perhaps the absence of one, brings us face to face with one of the deepest puzzles in all of science, the singularity. The concept of a singularity conjures visions of boundless compression, unfathomable gravitational pull, and the collapse of our fundamental understanding of space, time, and substance. It's a point where the very formulas we use to describe the cosmos, those that explain planetary orbits and stellar behaviors, cease to function altogether. To grasp how we arrived at this idea, we need to travel back to 1915, when a man with unruly hair and penetrating insight wrote down a formula that would permanently reshape our view of gravity. That man was Albert Einstein, and the equation was part of his general theory of relativity. Einstein revealed that gravity is not merely a force pulling objects together. It is the warping of the very fabric of space and time, molded by mass and energy. Planets do not circle stars because of some invisible tug, but because the star's mass causes a depression in space-time, and the planet moves along that curve. But Einstein's groundbreaking theory carried with it a startling implication. If a sufficient amount of mass is concentrated into a small enough volume, space-time could bend so sharply that it loops in on itself, creating a black hole, a domain from which nothing, not even light, can emerge. At the black hole's core is what we call a singularity. According to Einstein's equations, this is a point where density becomes infinite and volume drops to zero. All the matter from a collapsing star compresses into this minuscule location. However, there's a significant issue. Physics cannot cope with the idea of infinity. Just like trying to divide by zero, it's not a solution. It's a breakdown. The singularity represents the limit of our current models, the point where the known equations fail and knowledge gives way to the unknown. Despite its abstract nature, the singularity is not just a theoretical artifact. It is a direct consequence of our most successful gravitational theory. But here's where the narrative takes a startling twist. If singularities do indeed exist, they bring with them a challenge so unsettling that it prompted physicists to propose a safeguard, the cosmic censorship hypothesis. Introduced in 1969 by the brilliant Roger Penrose, this hypothesis asks a deceptively straightforward question. Could a singularity ever exist unshielded? To clarify, in a standard black hole, the singularity is enclosed behind the event horizon, an invisible shell around the black hole. Once anything crosses that boundary, it's trapped forever. No data or signals from within can reach the outside world. The event horizon acts like a filter, concealing the chaos of the singularity from the rest of the universe. But what if, under specific circumstances, a singularity formed without this protective barrier? What if it was laid bare, naked, unhidden, and exposed to the universe? Such a naked singularity would unveil the deepest mysteries of space-time and expose the failure of physics in full view. The causal structure of reality could unravel, and the universe itself might no longer behave in predictable ways. Penrose's hypothesis argues that the universe prevents this from happening, that nature ensures every singularity is always hidden behind an event horizon. In this view, the cosmos has built-in safeguards to keep its most chaotic secrets sealed away. Yet, the question remains unresolved. Physicists have long debated this idea. Some theoretical models suggest that under exotic conditions, such as rapidly spinning black holes or unique forms of gravitational collapse, naked singularities might indeed form. Certain computer simulations even suggest that the cosmic censorship principle might not always hold. If such singularities can exist in the open, it wouldn't just be a strange footnote. It would signal a major flaw in our current understanding. It would mean that the universe occasionally discards its own rulebook. But there's another layer to this problem. If singularities mark the failure of Einstein's equations, could they also point the way toward a deeper, more complete theory of gravity, one that harmonizes general relativity with quantum mechanics, the physics of the incredibly small? Many physicists believe so. They hope that a future quantum theory of gravity, perhaps string theory or loop quantum gravity, will replace the infinite quantities of the singularity with something finite, manageable, and physical. In such a theory, the singularity might no longer be a point of infinite density, but rather a region governed by new, unknown laws. For now, however, the singularity remains concealed, and cosmic censorship remains an open question. Black holes continue to guard their mysteries tightly, locking them away behind event horizons, challenging us to discover how to break through. In recent times, progress in observational astronomy has brought us closer to these enigmatic giants. The Event Horizon Telescope succeeded in capturing the first image of a black hole's event horizon in the galaxy M87, a glowing ring of emission encircling the darkness of something immensely compact. Yet even this historic milestone is only a starting point. As future observatories improve, we may be able to study these cosmic abysses more closely and edge nearer to understanding what lies within. And here's the crux of the matter. The singularity isn't just an abstract problem for academics. It's a profound challenge to human comprehension, a place where logic falters, explanations fall apart, and the universe seems to whisper, "Not yet." Still, we persist, because every attempt to understand the singularity, every challenge to the boundaries of known physics, draws us a step nearer to something extraordinary, something about the fabric of space-time, and perhaps the essence of existence itself. Are singularities eternally hidden, locked away behind the cosmic veil? Or will we someday gaze directly into their raw and chaotic core, seeing, finally, the universe stripped to its most fundamental truths? For now, the singularity remains an unresolved riddle, etched deep within gravity's shadow in the blackest reaches of space-time. And as long as that question remains unanswered, humanity will continue to explore, to compute, and to wonder, driven by the hope that one day we'll uncover what lies just beyond the edge of the universe's most profound secret. The fifth force of nature. Somewhere, nestled within the complex web of our cosmos, amid the intricate interplay of forces and particles, there may lie something more. For hundreds of years, scientists have crafted an immense theoretical framework built upon four foundational interactions: gravity, electromagnetism, and the strong and weak nuclear forces. Together, these four forces shape the behavior of everything, whether it's galaxies spiraling across the universe or the tiniest vibrations of atoms under our feet. And yet, even with their impressive track record in describing reality, these four core forces leave behind holes, mysteries unsolved, phenomena unexplained. This has led to a compelling question. Could a fifth fundamental force exist? The quest for this mysterious force didn't originate in futuristic labs filled with powerful particle accelerators or complex digital models. Instead, it began with something more traditional: gravity. In the early 1900s, Albert Einstein revolutionized the way we think about gravity with his theory of general relativity, redefining it not as a conventional force, but as the curvature of space-time itself. Yet, despite the power of Einstein's framework, it fits awkwardly with the laws that govern the universe on its smallest scales, where quantum mechanics dominates. In that quantum domain, gravity appears almost misplaced, like a relic from an earlier era trying to find its footing in a modern narrative. Scientists began to confront a troubling realization. Our most successful theories, the sweeping scale of general relativity and the microscopic rules of quantum physics, don't align. They exist as two separate languages, unable to communicate. And it is in this silence, this rift between the vast and the minuscule, that the first murmurs of a fifth force began to surface. In 2015, within the laboratories of the Atomiki Institute in Hungary, a research team led by Attila Krasznahorkai made an unexpected discovery. While analyzing the decay patterns of an excited beryllium-8 nucleus, they noticed something odd, a small but significant anomaly, an unusual signal in their measurements that suggested the presence of an unknown particle. This unexpected particle, if verified, could represent something groundbreaking, a mediator of a new fifth force. They dubbed it the X17 particle, a hypothetical boson weighing roughly 17 mega-electronvolts. If this particle is real, it could indicate a previously undiscovered force, one that delicately interacts with matter in ways never before observed. Still, scientific progress demands caution. Bold claims must be backed by equally strong evidence. If the X17 particle is indeed a messenger of a new force, then what is the nature of this force? Some scientists propose that it may serve as a link between known matter and the unknown, a dark force that primarily interacts with dark matter, the invisible substance believed to constitute approximately 85% of the universe's total mass. In such a case, this fifth force could do more than just tweak our understanding of atomic physics. It might provide insight into one of the most elusive aspects of cosmology, but the potential implications extend even further. A fifth force might help clarify puzzling galactic behaviors, like unusual rotation patterns or odd gravitational lensing effects. It could even shed light on the subtle irregularities in the universe's expansion rate. Such a force might knit together disparate threads of physics into a more unified, coherent picture of reality. However, the path to discovery is riddled with obstacles. The irregularity noticed at Atomiki has not yet been conclusively replicated by other research teams, and the X17 particle itself has remained evasive. Alternative experiments, including those at the Large Hadron Collider and high-precision atomic clocks, are actively probing the subatomic realm for traces of this elusive force, but none have yet provided definitive proof. Still, science thrives at the frontier of the unknown. Many concepts once considered outrageous, the bending of space-time, the principle of uncertainty, the dual-wave particle nature of light, were born from strange experimental results, small signals buried in data, calling researchers to take a closer look, to challenge assumptions, and to push boundaries. If this fifth force does exist, it could fundamentally reshape the laws that underpin our understanding of the universe. It may demand new models, new tools, and possibly a fresh perspective on the nature of existence itself. But even more significantly, it would serve as a powerful reminder that the universe still holds secrets in the open, hiding in plain sight, waiting for us to discover them. As it stands, the fifth force remains a tantalizing unknown, a compelling puzzle lingering at the margins of science. Somewhere, perhaps in the fleeting traces of particle interactions or in the slow, graceful motion of distant stars, the answer may be waiting. And whether it comes to light tomorrow years from now, or in a future era we can't yet imagine. One truth endures. The universe always has more to reveal. It never ceases to surprise us. Neutrino oscillations and anomalies. In the still, shadowed regions of space, where starlight fades into the boundless black and particles drift without sound through the expanse, there exists a mystery so deep that it questions the core of our grasp on existence. This puzzle begins with the neutrino, a particle so ephemeral, so intangible, that countless numbers of them are streaming through your body this very instant without leaving the faintest mark. Neutrinos are like cosmic specters, carrying messages from stellar cores, from the explosive deaths of stars, and from the universe's most extreme environments. Yet, despite their overwhelming presence, despite being virtually everywhere, they remain among the most puzzling entities in all of physics. Our journey into this enigma begins in the 1930s with a troubling inconsistency that perplexed scientists like Wolfgang Pauli. During radioactive decay experiments, researchers noticed a troubling pattern. The energy output didn't add up. It seemed that part of the energy was simply vanishing. In an attempt to save the foundational laws of physics, Pauli introduced a radical proposal. What if an invisible particle existed, one so tiny and so reluctant to interact with matter that it slipped by unseen during radioactive decay? He named this hypothetical particle the neutrino, Italian for little neutral one. At the time, the idea seemed nearly impossible to test. Neutrinos carry no electric charge, have almost no mass, and interact so feebly with matter that they could pass through a light year's worth of lead without slowing down. But in 1956, scientists Clyde Cohen and Frederick Raines finally captured evidence of neutrinos using a nuclear reactor. These ghost-like particles were real, yet this was merely the beginning. As decades passed, neutrinos revealed even stranger properties than anyone had imagined. Researchers discovered that neutrinos come in three forms, each connected to a different fundamental particle: the electron neutrino, the muon neutrino, and the tau neutrino. And here's where the mystery deepens even further. Neutrinos, it turns out, are capable of transforming from one type to another as they move. This surprising behavior is known as neutrino oscillation. Picture firing a stream of neutrinos across space. Though they may begin as pure electron neutrinos, by the time they arrive at a distant detector, some will have shifted into muon neutrinos, and others into tau neutrinos. It's as if these particles are in a constant state of flux, unable to settle on a single identity, continuously reshaping themselves as they voyage through the universe. But this leads to a contradiction. The standard model of particle physics tells us that neutrinos should have no mass. They should move at the speed of light, unburdened by inertia. However, oscillation between types is only possible if neutrinos do have mass. Without it, their flavors couldn't change. They'd remain fixed in one state forever. This discovery exposes a fundamental flaw in the standard model. Neutrinos demonstrate that our most trusted physics framework is incomplete. They are cracks in the very base of one of science's most revered theories. But the saga doesn't end here. Neutrino research has also uncovered oddities, baffling outcomes that suggest something deeper is still hidden, something beyond our current reach. Take, for instance, the solar neutrino problem. The sun, powered by nuclear fusion at its core, should release enormous numbers of electron neutrinos. Massive underground observatories, such as Super Kamiokande in Japan and SNO Sudbury Neutrino Observatory in Canada, were built to detect these elusive solar travelers. But when the data was gathered, a major discrepancy appeared. Only 1/3 of the expected electron neutrinos were being detected. The rest, 2/3 seemed to vanish en route from the sun to Earth. Eventually, the answer was found in neutrino oscillation. The electron neutrinos were not missing. They were transforming into muon and tau neutrinos, types that the detectors of that era couldn't detect. The mystery had an explanation, but the implications were monumental. Neutrinos not only possess mass, they behave in ways that fundamentally defy our established understanding of subatomic physics. And then there are the reactor neutrino anomalies. In carefully controlled experiments designed to analyze neutrinos produced by nuclear reactors, scientists noticed another strange trend: a consistent shortfall in the number of neutrinos observed compared to predictions made by theory. This led some physicists to hypothesize a fourth kind of neutrino, a sterile neutrino. Unlike the three known types, sterile neutrinos wouldn't interact with matter at all, except through gravity. These would be even more elusive, even less detectable, than their already near invisible cousins. If sterile neutrinos exist, they could potentially resolve some of the largest open questions in modern physics. They might be connected to dark matter, the unseen framework around which galaxies form. They could shed light on why the universe contains so much more matter than antimatter, instead of being a void filled with energy alone. But detecting sterile neutrinos is like trying to catch a whisper in the middle of a storm. Experiments such as Diabase, Minos, and IceCube have searched for subtle signs of their presence. While some hints have surfaced, conclusive evidence remains just out of reach. Each discovery about neutrinos feels like peeling back a layer, only to find another riddle underneath. These particles act as messengers from hidden dimensions of the cosmos. They emerge from stellar cores, from the explosive births of supernovae, and from nuclear reactions right here on Earth. They drift effortlessly through planets, stars, even black holes, carrying clues about the most extreme forces in nature. They are both astonishingly common, filling the universe in unimaginable numbers, and deeply bizarre, refusing to align with our standard theories. Yet perhaps the most compelling thing about neutrinos isn't their invisibility or their shape-shifting nature. It's the questions they inspire. Why do they have mass? Could there be more types we haven't found? Might they link to dark matter, the unseen mass of the cosmos? In every detector embedded deep in the Earth, in every beam launched between continents, scientists continue to listen. They search for tiny glimmers of light, subtle pulses in their instruments, signs that another piece of the puzzle is coming into view. The universe, it seems, speaks in quiet murmurs, and neutrinos, these silent, elusive messengers, are among the faintest voices of all. But if we can tune into them, if we can decode what they're saying, they might reveal a narrative unlike any we've encountered before, a tale about the true nature of existence, the hidden symmetries of reality, and just maybe, the ultimate destiny of the cosmos itself. Supersymmetry. Within the concealed framework of the cosmos, where particles engage in intricate motion and forces intertwine to form the tapestry of existence, physicists have long sought something extraordinary, an idea capable of imposing structure upon disorder, clarity upon complexity, and equilibrium upon the most foundational laws of the universe. They have named this profound concept supersymmetry. At a superficial glance, our universe appears wildly unbalanced. Matter vastly outweighs antimatter. Galaxies rotate with perplexing velocity, suggesting the pull of unseen dark matter. And the four fundamental forces resemble mismatched pieces forced together in an awkward union. Yet despite this seeming disarray, researchers suspect there is a deeper symmetry at work, a hidden unity linking every particle in the cosmos. To appreciate why supersymmetry holds such appeal, we must revisit the standard model of particle physics. This is the most extensively verified scientific framework ever developed to explain phenomena on the smallest of scales. It details quarks, which make up protons and neutrons, leptons, including electrons and neutrinos, and force carriers such as photons, gluons, and the W and Z bosons. At the center of this structure lies the Higgs boson, a vital component responsible for bestowing mass upon other particles. But for all its successes, the standard model is not without flaws. It cannot account for dark matter, the mysterious substance believed to comprise roughly 85% of all matter. Nor does it explain gravity, the force that shapes galaxies, powers stars, and binds solar systems. And perhaps most unsettling of all, the model portrays a universe perched on a knife edge, so precisely calibrated that even minute deviations could unravel the fabric of reality. This is where supersymmetry enters the scene. At its core, the theory offers a concept of remarkable simplicity and beauty. It proposes that every fundamental particle we know has a corresponding superpartner, a hidden relative with slightly altered characteristics. Fermions, like quarks and electrons which constitute matter, would have bosonic superpartners, and bosons, which mediate forces, would in turn have fermionic counterparts. These hypothetical counterparts are given distinctive names. Quarks would be paired with squarks, electrons with selectrons, and photons with photinos. Initially, this doubling of the particle family might sound like the fevered imagination of a theoretical physicist. Yet supersymmetry isn't about cluttering the particle zoo. It's about restoring symmetry. The interplay between particles and their supersymmetric partners would elegantly resolve mathematical divergences that currently disrupt the standard model. For instance, the mass of the Higgs boson, without supersymmetry, would shoot to unrealistically high values, tearing apart the theory's mathematical structure. But if supersymmetry holds, these infinite values cancel out, and the calculations regain coherence. One of the most tantalizing aspects of supersymmetry lies in its potential to explain dark matter. Among the predicted superpartners is the neutrino, a stable, uncharged particle. If it exists, it may be the very particle that makes up dark matter, a physical object floating through space, imperceptibly binding galaxies with its unseen gravitational influence. However, there's a major complication. Despite decades of dedicated searches, no superpartners have been found. The Large Hadron Collider LHC, the most powerful particle accelerator ever constructed, was expected to be the tool that would finally uncover them. Since its activation in 2008, scientists have hurled protons into one another at incredible speeds, hoping the collisions would reveal traces of these mysterious superparticles. But test after test, data set after data set, has come up empty. The superpartners remain hidden, if they exist at all. This absence of evidence has caused a quiet but growing unease in the physics community. Supersymmetry is a mathematically consistent and intellectually appealing framework. It promises answers to some of the most perplexing mysteries in science. But science is not swayed by elegance, only by evidence. And that evidence has proven elusive. Some researchers have recalibrated their expectations. Perhaps superpartners aren't as light as once assumed. Maybe even greater energy levels are required to expose them. Others speculate that supersymmetry may not be a universal truth, but a broken symmetry, like a cracked mirror that still reflects a coherent design. And still others have begun to entertain the possibility that supersymmetry, despite its appeal, could be incorrect. But the story of physics teaches a valuable lesson. Nature rarely gives up its secrets easily. Consider the Higgs boson, theorized decades before its confirmation in 2012. or neutrinos, once deemed impossible to detect, and now routinely studied. The cosmos seems to delight in keeping scientists guessing. Even if supersymmetry proves false, the pursuit has already reshaped physics. The hunt for these concealed particles has stretched the boundaries of high-energy physics, inspired technological innovation, and opened new paths of theoretical inquiry. Yet what if supersymmetry is true? What if buried in the reams of data from the LHC, there's a subtle signal, a trace of a squark, a lepton, or a photino? What if dark matter isn't a vague concept, but a vast sea of supersymmetric particles streaming through space and through us, forever silent? The implications are staggering. A verified supersymmetry wouldn't be just another scientific development. It would represent a seismic shift in our understanding of the universe. It would mean that the cosmos is not fundamentally chaotic or fragmented, but woven with an underlying symmetry. It would prove that dark matter isn't some theoretical placeholder, but a tangible, measurable part of existence. Right now, the search goes on. Accelerators rumble beneath the surface of the Earth. Detectors scan the silence of space. Scientists remain vigilant, waiting for the signal, the flicker of insight that could expose the symmetry concealed beneath reality's surface. Supersymmetry may be just beyond the horizon of our knowledge, hidden in plain sight, waiting for us to look closer, reach further, and imagine more boldly. And if it's out there, if this elegant symmetry is real, it will not only redefine our grasp of particles and forces, it will transform our understanding of the universe itself, a cosmic truth etched into the smallest constituents of matter, waiting to be discovered. Magnetic monopoles. Magnetic fields permeate the universe. They guide birds across continents during migration, shape the shimmering auroras that ripple through our skies, and wrap around stars and entire galaxies like invisible strands of force. Yet there's something curiously unbalanced about them, something fundamentally lopsided. Every magnet we know has two poles, a north and a south. If you break a magnet in half, you won't get a solitary pole. Instead, you'll end up with two smaller magnets, each still containing both a north and south pole. No matter how many times you divide it, the poles refuse to separate. And yet, when physicists describe magnetism through mathematical equations, there's no law that forbids the presence of a single, standalone magnetic pole, a magnetic monopole. It's as if the universe is quietly withholding a missing element of a much larger picture, a single puzzle piece absent from our understanding of nature's forces. If magnetic monopoles are real, they wouldn't just satisfy a theoretical curiosity. They could unravel deep truths about the structure of reality itself. Still, in nearly 100 years of searching, we haven't found one. Not yet. The journey begins in the 1800s with James Clerk Maxwell, one of the most brilliant minds in physics. Maxwell's groundbreaking equations brought together electricity and magnetism into one elegant framework. These equations showed that electric charges, such as electrons and protons, can exist independently. An electron possesses a negative charge, and a proton holds a positive one. But magnets? They seemed different. Maxwell's math insisted that magnetic poles must always come in pairs, northbound to south, eternally inseparable. Then in 1931, physicist Paul Dirac, quiet and profoundly reflective, uncovered something odd while working with quantum theory. Dirac found that if even a single magnetic monopole existed somewhere in the universe, it could resolve one of physics' enduring mysteries. Why electric charge is always found in tiny, exact amounts. Why every electron carries precisely the same charge. Why every proton matches it perfectly, but in opposite sign. Dirac's realization was astonishing. Just one magnetic monopole, hiding in the cosmos, could account for a universal feature of every charged particle. It was as if nature had encoded its most intimate laws in invisible ink, and Dirac had managed to glimpse a few faint lines. But there was an issue. No one had ever observed a magnetic monopole, and physics, despite all its beauty, remains an empirical science. It demands proof. As time moved forward, the idea didn't disappear. In the 1970s, theorists such as Gerard 't Hooft and Alexander Polyakov demonstrated that magnetic monopoles were not just possible oddities. They were an unavoidable consequence of grand unified theories, efforts to merge the electromagnetic, weak, and strong nuclear forces into one comprehensive system. According to their models, magnetic monopoles could have been born in the universe's first moments, right after the Big Bang, when the cosmos was a seething cauldron of energy and particles. But if that's true, if monopoles were forged in that early chaos, why haven't we found them? One theory is that they're simply extremely rare. So rare that, as the universe expanded, they became scattered across vast cosmic distances, each one isolated, drifting alone through space. Another idea is that they're massive, so heavy that our most powerful particle accelerators have no chance of producing them. Some estimates suggest a single magnetic monopole could outweigh a proton by billions of times. If such a particle were to travel through Earth, it would barely register, leaving behind only the faintest trace in our detectors. Then something remarkable happened. On February 14, 1982, physicist Blas Cabrera was conducting an experiment with a superconducting loop, a special ring of wire cooled near absolute zero, designed to catch the subtle signal of a monopole passing through. On that Valentine's Day, his instrument recorded a blip, a single perfect spike, the kind of event that would be expected if a magnetic monopole had passed through. It was a thrilling moment. For a brief time, it felt like physics had brushed up against something extraordinary. But that specific signal never occurred again. Other researchers, using similar methods, found nothing. Cabrera's reading became one of science's great unexplained events. Was it a moment of discovery? Or merely a technical anomaly? An echo from the machine? Today, the quest continues. Scientists have constructed enormous detection systems, buried deep below the Earth, spread across icy terrains, all in hopes of capturing that unmistakable sign of a monopole. Some researchers are turning their gaze toward the stars, speculating that monopoles might be trapped inside neutron stars or lurking in the remnants of stellar explosions. There's even conjecture about entire monopole stars, hypothetical celestial bodies dominated by magnetic charge, warping space around them. Still, despite our tools and theories, the universe offers only silence. No monopole has shown itself. And yet, if these elusive particles do exist, they could rewrite everything. They might help explain the symmetry linking electricity and magnetism. They might bring us closer to a unified picture of nature's forces, or give us insight into the very birth of the universe, when time and space were still taking form. Perhaps they could even offer hints about dark matter, the hidden substance that holds galaxies together. It's a strange notion. Somewhere, silently drifting through the endless void, a single magnetic monopole might be gliding, an ancient traveler carrying with it answers to some of the most profound questions ever asked. For now, our detectors remain quietly alert in the dark. Our equations linger on blackboards and within scientific journals. And once in a while, a physicist pauses, wondering whether the universe is guarding its secrets just out of reach, or whether the clues are already here, buried within the static, waiting to be uncovered. If even one magnetic monopole exists, It may already be in motion, sailing through interstellar space, crossing stars, planets, and comets, bearing a secret that predates everything we know. And maybe, just maybe, one day, it will pass through our instruments, and in that instant, the cosmos will no longer whisper its secret. It will answer, clearly and unmistakably, with one single, perfect magnetic pulse. The neutron lifetime enigma. In the vast symphony of the universe, neutrons are the soft-spoken instrumentalists, small, modest particles residing deep within atomic nuclei, playing an essential part in maintaining the fabric of matter. Without them, stars wouldn't blaze, atoms would unravel, and the universe as we perceive it would never have come into being. Yet, there's an unsettling conundrum surrounding these modest subatomic entities. When they are released from the secure confines of the nucleus, neutrons encounter a kind of identity crisis. They undergo a quiet, unavoidable transformation, decaying into protons, electrons, and neutrinos in a process known as beta decay. Here's where things become strange. Physicists can't seem to agree on exactly how long it takes for this process to occur. This is the heart of the neutron lifetime enigma, one of the most stubborn and bewildering puzzles in current physics. There are two main techniques used to determine the lifespan of a lone neutron, two strategies that, in principle, should give matching outcomes. But they don't. Instead, they consistently diverge by approximately 9 seconds. 9 seconds might not seem critical, but in the razor-sharp world of particle physics, that's a massive divide, wide enough to suggest something more profound at play. Is it a flaw in our experimental setups? A minute factor we haven't accounted for? Or could it be evidence of unfamiliar physics, lying just out of reach? To make sense of this, we must venture into the miniature domain of fundamental particles, where forces far more powerful than anything we experience daily hold atomic nuclei together. Neutrons, in this microscopic arena, act like a kind of atomic glue. Within a nucleus, they're steady, bound tightly with protons by the mighty strong nuclear force. But take a neutron out of that environment, remove it from the protective company of its atomic companions, and it becomes unstable, ticking toward its inevitable transformation. On average, a solitary neutron lasts about 15 minutes before breaking down into a proton, an electron, and an antineutrino. But how can we measure the lifetime of something so transient, so tiny, and so invisible to our senses? Physicists have designed two key approaches, the bottle method and the beam method. In the bottle method, researchers capture neutrons within a specially constructed magnetic or gravitational chamber, an unseen bottle that prevents them from escaping. Over a period of time, scientists tally how many neutrons are left and determine the average time before decay occurs. This approach yields a neutron lifespan of around 879.9 seconds. The beam method takes a completely different route. In this setup, free neutrons are streamed through a detector, which tracks how many protons emerge from neutron decays. Using those numbers, researchers calculate the neutron's average life indirectly. The outcome? A slightly longer lifetime, approximately 888 seconds. These two measurements are supposed to match. After all, the universe shouldn't operate under one rule for neutrons in a bottle and a separate rule for neutrons in a beam. Yet no matter how many times these experiments are conducted, the contradiction persists. For years, scientists have triple-checked their math, refined their instruments, improved their procedures, and eliminated every obvious source of experimental error. And still, the 9-second divide remains. suspended in uncertainty like a riddle without an answer. At first glance, it might seem like a simple technical mismatch, an issue to be solved with better equipment. But some researchers are beginning to suspect something far deeper, that this inconsistency could hint at new physics, hiding just beyond our current understanding. One possibility? That neutrons may not always decay into the familiar trio of proton, electron, and antineutrino. They might, on rare occasions, decay into something else, something unseen, something we haven't yet detected. Perhaps sometimes, a neutron disappears into an unknown particle, possibly a candidate for dark matter. If true, it would mean that every neutron lifetime experiment has unknowingly been catching fleeting glimpses of a hidden realm, a brief interaction with an unseen part of the cosmos. Another theory proposes that this discrepancy might highlight a gap in our knowledge of the weak nuclear force, the fundamental force responsible for beta decay. Could it be that the equations we use, the foundational assumptions, are missing something? A correction? An unknown interaction? The implications are enormous. If neutrons can decay into dark matter, it wouldn't just clear up the lifetime debate. It could cast new light on one of the biggest questions in modern astrophysics, the nature of dark matter itself. But bold claims require solid proof. At the moment, this neutron lifetime gap remains an unresolved anomaly, a persistent irregularity that refuses to disappear. To solve it, researchers are creating more advanced experiments, with even more meticulous controls and greater accuracy. They're constructing enhanced neutron traps, refining beamlines, and developing detectors that can capture the subtlest traces of particle activity. And while the search continues, the universe remains quiet, because the neutron lifetime isn't just some obscure number in a physics textbook. It's a fundamental constant that affects the very makeup of our universe. It plays a critical role in the Big Bang nucleosynthesis, the cosmic process that produced hydrogen, helium, and lithium in the minutes following the universe's birth. Get the neutron's lifespan wrong, and our entire model of the early cosmos starts to falter. And so, we stand at the edge of an open question: two measurement techniques, two outcomes, and a single enigma. Within that unexplained 9-second window might lie a hidden truth, an extraordinary clue waiting to be uncovered. Maybe the answer lies in particles we've never seen, in forces we haven't yet grasped, or in untouched territories of natural law. Or maybe, as with so many profound mysteries in science, the key is simply waiting for our tools to catch up, or for a brilliant thinker to see the signal hidden within the static. For now, neutrons continue their quiet existence, in sealed bottles, in controlled beams, within stars, and across laboratory chambers. They decay in silence, disappearing moment by moment against the vast expanse of time. And somewhere within those nearly invisible seconds lies an answer. If we can uncover it, we may find that it changes everything we thought we understood about the universe. The fine-tuning puzzle. At first glance, the cosmos appears vast, wild, and impersonal. Galaxies crash into one another, stars erupt in violent explosions, and black holes silently swallow all that strays too near. Yet, hidden beneath this grand display lies something even more astonishing: an underlying harmony, a network of cosmic settings aligned with breathtaking precision. If these cosmic parameters were altered even slightly, even by an almost immeasurable amount, the universe as we know it would simply not exist. No galaxies, no stars, no planets, and certainly no human beings. This is what's known as the fine-tuning problem, a central and deeply puzzling question in both physics and cosmology. Why does our universe appear so precisely suited for life? Is it sheer luck, absolute necessity, or is there something even more profound behind it all? To delve into this mystery, we must first acknowledge a foundational truth. The physical laws that govern our universe are not random. They're mathematical, elegant, and defined with an extraordinary level of precision. They govern everything, from nuclear fusion inside stars to the subatomic interactions in a molecule of water. But these laws don't act alone. They rely on certain basic constants, specific numbers embedded in the fabric of nature that control how everything behaves. Take, for instance, the gravitational constant. It determines the strength of gravity, the force that holds together everything from planets to entire galaxies. If gravity were just slightly stronger, stars would burn up their fuel far too quickly, collapsing into black holes long before any planets or life could emerge. If gravity were weaker, stars might never form in the first place, and the cosmos would remain cold and empty, a scattered sea of hydrogen. Or think about the strong nuclear force, which binds protons and neutrons inside atomic nuclei. If it were only a bit weaker, atoms heavier than hydrogen wouldn't form at all. No carbon, no oxygen, none of the essential ingredients for life. Then there's the cosmological constant, an enigmatic form of energy that causes the expansion of the universe to speed up. Its value is so minutely tuned that a slight increase or decrease would have resulted in a cosmos that either collapsed upon itself or expanded too rapidly for stars and galaxies to take shape. Each one of these constants is like a knob on an impossibly intricate machine. And somehow, each is turned to just the right setting. Adjust even one dial by a hair's width, and the universe becomes uninhabitable, empty, dark, or non-existent altogether. This incredible level of fine-tuning raises an unnerving question. Is this perfect balance merely an accident? A one in a trillion chance? Or is something more at work? This is a question that scientists, philosophers, and theologians have long wrestled with. Their answers span from the scientific to the spiritual. One idea is known as the anthropic principle. It proposes that we shouldn't be shocked to find ourselves in a universe capable of sustaining life, because if the universe weren't capable of supporting life, we simply wouldn't be here to ask the question. In other words, our very presence implies that the universe must have had the right conditions. While logically sound, the anthropic principle doesn't satisfy everyone. It doesn't explain why the settings are what they are. It merely points out that they had to be this way, or else we wouldn't be around to notice. Another concept is the multiverse hypothesis. What if our universe is just one among an endless collection of universes, each with its own distinct laws and constants? In most of those hypothetical universes, the settings might be completely incompatible with life, chaotic, empty, or doomed to instant collapse. But in a limitless ensemble of universes, it's inevitable that a few will happen to have just the right combination of factors for life to emerge. And we naturally exist in one of those rare universes. It's a compelling theory, but it has a serious drawback. There's no experimental proof. We've never observed these other universes. The idea sits on the edge of science, leaning precariously between theoretical framework and pure speculation. Still, many physicists view it as one of the most promising explanations. There's also a more poetic possibility. What if the universe wasn't randomly fine-tuned at all, but was always destined to be this way? What if these physical constants are not arbitrary, but arise naturally from some deeper, unified principle, an elegant and undiscovered equation that governs all of reality? In this interpretation, the universe had no other choice but to be finely tuned. These constants aren't lucky, they're necessary. This would mean our universe isn't an accident, but the inevitable consequence of a deeper symmetry, one we've yet to uncover. But perhaps the most sobering thought is this: maybe we'll never know. Maybe the fine-tuning question is a permanent enigma, a riddle whispered between galaxies, never to be unraveled. Still, one thing is certain: we exist on a precarious edge. Every star that burns, every breath we take, every fleeting moment, all of it depends on the delicate calibration of these cosmic parameters. It's a reminder of just how improbable and fragile our universe really is. A mathematical symphony where each note is struck with perfect pitch. And yet, somehow, here we are, questioning, exploring, and reflecting on our own existence. Somewhere, within equations we've yet to solve, or in the light from ancient galaxies, an answer may already be hiding, whether it lies in quantum fluctuations, an infinite multiverse, or in the elegance of a law not yet known. The fine-tuning mystery forces us to face something deeply humbling. This universe isn't just a random explosion of matter and energy. It's a place defined by astonishing precision. For now, we can only marvel at the balance, at the razor's edge upon which existence rests, at the dials, so impossibly set, as though the cosmos itself is holding its breath, waiting for us to notice. In the vast corridors of time and space, beneath the gleam of stars and the hush of the void, we find ourselves standing between certainty and wonder. The fine-tuning mystery isn't just a scientific question. It's a powerful reminder of how rare, how brief, and how precious life truly is. And perhaps, just perhaps, the universe was calibrated with care, so that one day, somewhere, on a fragile blue sphere orbiting a modest star, we would awaken to see it. Neutrino oscillations. In the silent reaches of the cosmos, where light from stars dims into infinite blackness and particles quietly drift across the emptiness, there lies a mystery so deep it unsettles our very grasp of existence. It all starts with the neutrino, a particle so intangible, so ghost-like, that countless numbers of them are passing through you right now without leaving even a mark. Neutrinos are cosmic shadows, conveying messages from the cores of stars, from the explosive death throes of supernovae, and from the most extreme environments in the universe. And despite being everywhere, despite their omnipresence, they remain among the most puzzling subjects in all of physics. The story starts in the 1930s with a dilemma, a puzzle that confounded physicists like Wolfgang Pauli. During studies of radioactive decay, scientists noticed a problem. The energy output wasn't adding up. Some of it seemed to vanish without explanation. Pauli, determined to safeguard the established laws of physics, offered a daring idea. He suggested that a previously unknown particle was escaping detection, a particle so tiny and reluctant to interact that it simply disappeared unnoticed during radioactive processes. He named it the neutrino, meaning little neutral one, in Italian. At the time, it seemed nearly impossible to confirm. Neutrinos carry no electric charge, possess almost no mass, and interact with matter so rarely that they could fly through a solid light year of lead and not even slow down. But in 1956, physicists Clyde Cohen and Frederick Raines managed to detect them during a nuclear reactor experiment. These invisible particles were real, but that discovery was just the first chapter. Over the years, neutrinos proved to be far stranger than expected. Physicists found out there aren't just one, but three types of neutrinos, each linked to a different particle: the electron neutrino, the muon neutrino, and the tau neutrino. And here's where the mystery deepens. As neutrinos travel, they can switch identities. This behavior is known as neutrino oscillation. Imagine firing a beam of neutrinos across space, starting with pure electron neutrinos. By the time they arrive at the other end, perhaps millions of kilometers away, some have changed into muon neutrinos, while others have become tau neutrinos. It's as if these particles live in a state of constant transformation, uncertain of what form they'll take, endlessly shifting as they move through the universe. But there's a problem. According to the standard model of particle physics, neutrinos should have no mass at all. The theory asserts they should race through the universe at light speed, unburdened by mass. Yet this shape-shifting behavior, this oscillation, requires that neutrinos do have mass. Without mass, they couldn't change types. They would remain fixed in a single form forever. This simple fact, neutrinos having mass, proves that the standard model, once thought complete, is not. Neutrinos expose a weakness in one of science's most carefully built frameworks. But the enigma doesn't stop there. Experiments involving neutrinos have also produced anomalies, strange, unexplained findings that point toward an even deeper layer of reality we've yet to comprehend. Consider the solar neutrino problem. Deep in its core, the sun fuels itself through nuclear fusion, a process that should generate a massive number of electron neutrinos. To catch these ghostly messengers, scientists constructed enormous underground detectors like Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada. But when data arrived, something was wrong. Only about 1/3 of the expected neutrinos were being detected. The other 2/3 seemed to vanish between the sun and Earth. The explanation, again, was neutrino oscillation. As they traveled, electron neutrinos were changing into muon and tau types, which early detectors weren't built to observe. The puzzle was solved, but the consequences were profound. Neutrinos not only have mass, they behave in ways that shake the foundations of particle physics. Then came the reactor neutrino anomalies. In controlled experiments using nuclear reactors to study neutrinos, physicists noticed another discrepancy. Fewer neutrinos were being observed than predicted by theory. This recurring shortfall led some to propose a radical solution, a fourth kind of neutrino, called the sterile neutrino. Unlike the known three types, sterile neutrinos wouldn't interact with matter at all, apart from their gravitational pull. They would be even more intangible, even more elusive than their already spectral siblings. If sterile neutrinos exist, they could help solve some of the biggest puzzles in physics. They might contribute to our understanding of dark matter, the hidden mass that binds galaxies together. They could also shed light on the mystery of why our universe is filled with matter instead of being wiped out by equal amounts of antimatter. Yet detecting sterile neutrinos is no easy task. It's like trying to catch a whisper in the middle of a storm. Experiments like Diabae, Minos, and IceCube have all searched for their faint signals. Though hints have emerged, no definitive evidence has been found. Every time we learn more about neutrinos, it seems we uncover a new mystery behind the one we just solved. These particles are messengers from realms beyond our reach. They are born in the blazing furnaces of stars, in the violent deaths of supernovae, and inside the cores of nuclear reactors. They pass effortlessly through stars, through planets, even through black holes, carrying clues about the most extreme environments in existence. In a sense, neutrinos are both utterly common and utterly strange. They fill the universe by the trillions, yet refuse to conform to our current understanding of physics. But perhaps what's most astonishing isn't just their ghost-like behavior, or their ability to change form. It's the questions they force us to confront. Why do they have mass at all? Could there be more types of neutrinos waiting to be discovered? Might they connect to the unseen dark matter that permeates the cosmos? Across the world, in detectors buried deep in the earth, and in beams shot across entire continents, scientists are searching for answers. They watch for fleeting flashes of light, subtle pulses in their instruments, signs that might reveal one more secret. The universe, it seems, speaks in whispers, and neutrinos, these faint, spectral travelers, are among its quietest voices. But if we can tune into their message, if we can understand what they're telling us, they might lead us to a story unlike anything we've known before. A tale of the universe's hidden architecture, its unseen harmonies, and maybe, just maybe, its ultimate destiny.